Hey folks, good afternoon. I hope that you've had a successful day of revising or doing exams, whatever you've been doing. This is going to be a live stream going through everything that's going to be in GCSE Chemistry Paper 2. In a bit more detail than the pre-recorded video that's on my channel. So just to give you a heads up, in case you don't know what else is available on the channel, a few other things. If you don't have enough time to stick with us for this whole live stream this afternoon, because this is going to be an extended version, there is a pre-recorded version that's a little bit shorter. It's about an hour, which you can find at this address here. If you're wanting to make sure that you've covered all the key facts, then this address here is a bunch of recall questions for each of the topics. These links are case sensitive, by the way, so you need to get the capitals in the right place. And then for each set of those questions, there's a video that goes with them, which tells you all the answers. I've also made a new video this week, which is all the required practicals for this for this paper. And then also for each individual topic, there are specific summary videos. So if you're sort of particularly thinking that you want to revise organic chemistry or atmosphere or whatever it is without going through the whole paper, then those videos are there for you. So this live stream is going to be everything for triple science and combined science, foundation and higher. And if you keep an eye on the tags at the very top of the screen, any time that there's content that is only for higher tier or only for triple scientists, it does say up there, and I'll try and call it out again as well. So if you're taking combined science or if you're taking foundation, then you know which bits you kind of don't need to revise with us. So the very first topic that we need to cover is rates of reaction. So the rate of a chemical reaction is its speed, and we can measure that in two ways: either how quickly it uses up reactants or how quickly it makes products. And there are two formulae that you can use to calculate this, but they both have the same format. So either it's reactant used or it's product made, but either way it's divided by time. And this is a really important thing, that you can't calculate rate without a time. So if you're describing any reactions, any methods, you need to be talking about timing that reaction and recording that. So these can be in you can have the rate as grams per second or centimetres cubed per second. And then also, if you're taking higher tier, you could also be asked to calculate in moles per second. So just for an example of how we would use this, if we had a reaction that produced 20 centimetres cubed of gas in 2 seconds, then I would do 20 divided by 2, and that would give me 10 centimetres cubed per second, which is the mean rate for that reaction. Now, one thing to watch out for is that our units here are centimetres cubed. So in other words, a centimetre by a centimetre by a centimetre, right? That's part of the units. It's not part of the number. So when I do this calculation, I don't need to cube 20. I just use 20, and the cubed sign is just part of the units. If I wanted to collect data in terms of a mass change, then I would need to carry out my reaction on a balance, which is this. So you might be tempted to call this a scale, but our proper science word for it is a balance. So that's what we want to call for it. So this is going to work for reactions that release a gas as one of the products, because therefore the mass of the reaction is going to decrease. So that could be something where we've got some metal with some acid, in which case it would release hydrogen, or actually I've just realised that on this diagram I've labelled it as marble, which is calcium carbonate, so that would release carbon dioxide. But regardless, if a gas is being released, then we could measure the mass, and that would allow us to calculate a rate for it. I record my data in a table like this. It's important that the units are in the headers. So I've got grams written up here. I wouldn't have grams written down here. No, that would be a bad thing. So I only want the units up here in the header. And it's also really important that in my table I include 0 for a time, so I find out what was the mass before the reaction had started. And that's also going to be true if you're asked to plot some data on a graph. Really commonly people miss out the data point for where the time is 0, and they just sort of think it's not important. So make sure that you are including that. So what we're actually interested in is the change of mass, and it's important that we're always comparing it to the very start. So the first one of these is easy because the mass hasn't changed yet, and the second one is also easy because you can see it's gone down by 0.07 grams. But the place that people start making mistakes is with the next line of the table, because what we actually need to do is compare always to the start. So lots of people are going to accidentally compare to the one above, and they're going to say 0.05, but that would be wrong. We don't want to do that. We want to compare to the start. So we'd have 0.12 and then 0.16 and yada, yada, yada. So if you are measuring the mass change for a reaction so that you can calculate the rate, your overall mass change is always going to be going up, because you're not going to suddenly put some of that gas that escaped back into the reaction. So if your numbers don't keep on going up, then something's gone wrong. Alternatively, instead of measuring the mass change, you could collect the gas as it's released and then measure the volume there. So there are two different options that you can do. You can use a gas syringe, which is this piece of equipment that you can see in my picture here, and that's probably your best way of doing it, because it's going to give you really accurate data. And it's sort of relatively easy to use, but you may never have used one in school, because they're quite fragile, they're usually made of glass, and they're quite expensive to replace, and frankly a lot of schools don't trust their year 9s with them. So what you're more likely to have done is, this is called collecting gas over water. And it's where we've got a measuring cylinder that's full of water, and then as the gas comes out of this delivery tube here, so this is my conical flask where my reaction would happen, the gas would come through that delivery tube, and that delivery tube, if I was actually in the middle of doing the reaction, would go up here into the measuring cylinder, and as the gas came out, it would displace the water, it would push the water out, so I'd end up with a gas bubble forming up here, and as the bubbles came up, that bubble would get bigger and bigger, and I can measure the volume by reading it off the measuring cylinder. So that's your alternative. You need to be able to plot rate data onto a graph and also interpret graphs that the exam board have given you. So in case you weren't aware, for GCSE Chemistry, 20% of your marks are for math skills, and those have to be math skills that are hard enough. If you're taking higher tier science, the math skills have to be hard enough to be included in the GCSE Maths Foundation tier paper, if that makes sense. So this is one of the math skills they could test. Can you plot some data on a graph? So I'd start off, and as we say, we've got to make sure that we've included that point at 0, 0, and then we would add the rest of these in. And I would draw a line of best fit through those. It's important to remember, and I know this is different to what they teach you in GCSE Maths, your line of best fit should reflect whatever your data is doing. So here you can clearly see that my data is curving, and therefore my line of best fit also needs to curve. So the gradient of a graph of mass change over time or volume change over time can tell you the rate of the reaction, and essentially the steeper it is, the faster that reaction is going. Now we can actually work out some numbers for it, but also just qualitatively we should be able to say that's what's going on there. So in this instance, the reaction that's represented by the purple line has got a faster rate than the blue reaction, because the line has a steeper gradient. So I've just realised some people might be colourblind, but this line on top is faster, and if they asked me how I knew, I could say, well, at 10 seconds that had changed by 5, whereas this has only changed by about 2.5. Now you can also look at a curved graph and make similar conclusions. So here we can say that my reaction is going faster at the start, which is what we expect. Basically every reaction you meet at GCSE is going to go faster at the start because there are more reactants available, and then gradually as time has gone on it's slowed down. You could be asked to actually calculate the gradient of that graph. So obviously from your maths lessons, you know that we can calculate the gradient by doing the change in y over the change in x, or you might remember rise over run or something like that. But if I wanted to work out the average rate of reaction here, I would say, okay, it's used up 5 grams, I can see that here, and it's taken 10 seconds to do that. So again, I just use that same formula, and I find that 5 divided by 10 is 0.5. Now, if you've got a curved graph, firstly, we can calculate the mean rate of reaction, the average rate of reaction, and to do that, we just find out how much has that reaction used up, and we do exactly what we did before. But sometimes that's not going to be quite enough. Sometimes you're going to want to know what is the reaction at a particular, what is the rate of the reaction, sorry, at a particular time. So like, what is the rate here, or what is the rate here? We've said that that rate is changing over time. We can see that the graph is getting less steep, but it's very, very hard to work out the gradient of a curve. So we don't. What we do instead is we draw a line called a tangent, and that tangent touches the curve in just one place, and therefore the gradient of that curve will be exactly the same as the gradient of the tangent. So your tangent is going to give you the most accurate result if it's as long as possible. So I could have drawn a little tangent here that was just sort of that long, but that would make it very hard for me to accurately measure how tall it was and how wide it was. So you want to make this tangent as long as you possibly can, and you want it to only touch your curve in one place. If you don't have a transparent ruler, it's a good idea to put your ruler on top of the curve. Oh, sorry, that was a terrible drawing. Rather than underneath the curve, because that way you can still see the curve. So anyway, if I draw that tangent there at 4 seconds, I can then say, okay, so the mass has changed from 2 up to 9, which is 7, and that's taken 10 seconds to have, so therefore my rate is 0.7. And then here at 7 seconds, we said it's a little bit flatter. Again, I've drawn a tangent. This time it's gone up from sort of 4.5 to 6.5. I know that my graph is not super easy to read, but obviously the one in the exam is going to have far more sort of gradations so that you can actually see what's going on a little bit. So you'll have a clearer idea of what's going on there. So then we move on to collision theory. And collision theory is this idea that chemical reactions will only happen if the particles that are reacting collide with each other, so that means bang into each other, and also if they have sufficient energy. And we call that minimum amount of energy that they have to have the activation energy. So there are 5 different factors that can affect the rate of a reaction. So we've got pressure, concentration, surface area, temperature, and catalyst. You can increase pressure in 2 different ways. One is by increasing the number of particles in a container. So if you imagine about blowing up a balloon or blowing up a bike tyre. And the other is by making the container smaller, because the pressure is caused by the particles bouncing off the walls of the container they're in. So if they're in a smaller container, they're going to collide with the walls more frequently. So we would say that increasing the pressure will increase the rate because the particles will collide more frequently. And frequently is a super important word. You could also say more often, or you could say more times per second, but you can't just say more. And the easiest way to think about this is I could say to you, I'm faster than Usain Bolt because I ran 5 kilometres yesterday and he only ran 100 metres. And obviously that's complete rubbish, because even though he only ran 100 metres, he did it in 10 seconds, whereas my 5 kilometres took me a lot longer than 10 seconds. So it's not just enough to say that the particles are colliding more, because they might have taken a longer time to do it. It needs to be more frequently, more often, more times per second. So next up, concentration. So this is very similar to pressure, but it applies to solutions rather than gases. But it's the same idea. If the concentration increases, we have more particles in the same volume, so therefore they're more likely to collide. They collide more frequently, that important word again, and therefore we're going to have a higher rate of reaction. Next up is surface area. So as you cut an object into smaller pieces, you increase the surface area. And often that leads to a lot of confusion because people are thinking, well, it's one tiny particle, how can it have a bigger surface area? So we don't mean the one tiny particle has a bigger surface area. We mean if we've chopped up a big piece of, say, metal into lots of little bits, the surface area of all those bits put together. And the easiest way to visualise this is, I know this is in 2D, but if you imagine that this here is a piece of metal, so maybe this is some magnesium or something, and I'm putting it in some acid, and the acid can react with all these bits around the outside, but it can't get to here in the middle because it's sort of shielded. Whereas if I cut that magnesium into some smaller bits, then suddenly all these internal faces can also react. So again, we're going to say that our particles collide more frequently, and therefore the rate of reaction is higher. So next up, we need to think about temperature. So all of the particles that are in a reaction have a certain amount of energy, and we've said that they need to have a minimum amount called the activation energy in order to react. So this line here, this blue line, represents the activation energy, and in my reaction I've got 6 particles, and you can see that some of them have quite a lot of energy and some of them have not very much. So in this reaction, the 3 particles that have more energy than the activation energy would be able to react if they collided. But the other 3, even if they collided, no reaction would happen. So if I heat up a reaction, I am giving more thermal energy, and the particles are going to use that as kinetic energy. So they're going to move faster. But regardless, what they have is more energy. So they're going to move faster, they're going to collide more frequently, but also, if we give them all a bit of energy, now 4 of my particles have enough energy. They have the activation energy, where before it was only the 3 of them. So that's why increasing the temperature is going to increase the rate of reaction. There are two parts to it. There's the fact that they move faster, they have more energy, so they collide more frequently, and the fact that a greater proportion have got the activation energy, and therefore if they do collide, then they're actually going to react. So I've got distracted because I just tried to look at the comments and I was trying to read and talk at the same time, which is very silly of me. Okay, so then our last way that we can speed up rates of reaction is by introducing a catalyst. So a catalyst is a chemical. It has to be a chemical. I cannot tell you how many times people have written that high temperature or energy is a catalyst, and it's not. It has to be a chemical that you're adding in. And these chemicals speed up the rate of reaction without being used up or permanently changed themselves. So you can get that catalyst back after the reaction is finished. And enzymes are an example of a biological catalyst. So enzymes exist within cells and they speed up reactions within that cell or within that organism. So regardless of whether we're talking about chemical catalysts or biological catalysts, they provide an alternative pathway that has a lower activation energy. So if here is me and I want to go visit my friend, it's going to take me a certain amount of energy to climb up over the mountain. And if I don't have that energy, if I'm feeling a bit tired today, then I can't get there. It just can't happen. And in the same way, if a particle doesn't have enough energy, it just can't react. Whereas if I have an alternative pathway that's around the bottom of the mountain, it's not changing how much energy it takes to go over the mountain, it's just giving you an alternative way that takes less energy. And if you were drawing an energy profile diagram, which we did a lot of in Unit 5, Paper 1, we would mark the activation energy between the reactants and the transition state. It's always going there. But if there was a catalyst involved, then we would see that the activation energy is smaller. And I think certainly in the triple paper, we didn't have any reaction profiles in Paper 1, so there's a reasonable chance of them coming up in Paper 2. Okay, quick water break while I catch up the comments. Okay, so in answer to the question about whether this covers everything, even the pre-recorded video, which is sort of 60 minutes long, covers every point of the spec. I haven't skipped any sections, but what I obviously have to do is do some of it in not a huge amount of detail, because, you know, if it's taken you 2 or maybe 3 years to be taught this course, I can't possibly cram it all in. So this is going to be in quite a bit more detail. It's probably going to take me 2.5 hours, but evidently, like, I can't teach you everything that you've been taught in the last 2 or 3 years. So this is covering everything in combined science and triple, covering all of it, but there are headers at the top, and there haven't actually been any yet because we haven't covered anything yet that isn't just in combined foundation. But when we do get to that bit, then it will say at the top, and also I'll call it out. Also, no, this is not pre-recorded. I did pre-record the physics one, and then you all gave me such a hard time that I'm doing it live. That's why there's a lot more ums. How long is the combined bit of this? Well, I'm not doing combined and then triple at the end. I'm doing it in the order it's in the spec, because there are triple bits, mainly in units 7 and 8 and 10. So I guess if you're doing combined, then the last sort of 20 minutes or so, which is triple for Unit 10, you'll be able to skip off and not stay for. But it is kind of integrated and there's not a lot I can do about that. Yes, my last one was pre-recorded because it was physics. But yeah, people were not a fan about this. And is it true that AIDS is spread through touch? Not hugely relevant because we're not doing biology paper 1. But if you don't have blood-to-blood contact or bodily fluid to bodily fluid contact, I think you're going to be okay. Right, let's crack on then. So, first required practical. We've said already that the required practicals make up 15% of all the marks available. So if you find that you have one thing that you can revise, it needs to be the required practicals. So the required practical for Unit 6 investigates what happens to the rate of reaction when we alter the concentration of one of the reactants. It's important that you're only going to be changing one of them, because obviously if we change the concentration of both reactants, if it's 2 solutions, then that wouldn't give us valid data. In our primary school language, we would say it wasn't a fair test. So this is a 2-part investigation, because you have to investigate one reaction that collects gas. So like we mentioned before, here's my gas syringe. And then we've also got a second a second practical where we're investigating turbidity, and turbidity means cloudiness, but we'll worry about that in a second. Yes, iron wool is a chemical catalyst. Yes, it is for foundation too. If we're going to collect gas, it needs to be a reaction that will release gas. So it's usually going to be magnesium in acid or marble chips in acid. So there are two ways that we can do this, and we did mention these already. You can either collect gas over water by using an upturned measuring cylinder, or you can use a gas syringe. Whichever method you're describing, you need to make sure that you're talking about taking readings at regular time intervals. So measure the volume of gas that is produced every 5 seconds, or measure the volume of gas that's produced every 10 seconds, or whatever it is. Because this is a required practical, because this is an investigation, you need to make sure that you are clear and you can describe what are your independent variable, your dependent variable, and your control variables. So independent variable is the one that you are changing, which in this is going to be change in concentration, usually of some acid, although it could be not an acid. Dependent variable is whatever you are going to measure and observe. So here, it's effectively the rate. And then control variables are all the things that you are going to keep the same. I am a control freak, so I always have my lilac PowerPoint, I always have my classes sat in my seating plan, I always use the same font because I am a control freak. So if we were going to do different concentrations of acid, and we were putting in some magnesium, then I would change the concentration of the acid, but I would keep the same the volume, and I would keep the same the mass of the magnesium. You shouldn't ever, we quite often see people writing things about, oh, I'll keep the conical flask the same or something. The equipment that you're using is not going to be a control variable, because it needs to be something where if you changed it, it would change the results. And if I just washed up this conical flask and used another one, then that wouldn't affect the results that I'm going to get. A little vocabulary check thing. You've all done chemistry paper 1. You all hopefully know that amount means the number of moles, and very often when you think the word amount, you don't mean what chemists mean by amount. So by far the easiest way, particularly for paper 2, is to just ban the word amount from your vocabulary. If it is a solid, talk about the mass. If it is a gas or a solution or a liquid, then talk about the volume. Just do not use the word amount, because so often people say it when it's not what they mean, and then they can't have a mark. Okay, so then the second part of the required practical is a method that uses turbidity. So turbidity means cloudiness, and you can identify that this is a reaction, because they're not necessarily going to say to you using turbidity. You can identify that it's this sort of reaction because if you look in the symbol equation, which they have to give you because this isn't a named example, you don't have to know about this reaction, but it's just, there are basically only 2 reactions with turbidity that we do in Key Stage 4, so you're almost certainly going to have done this one. The way you can tell is that you've got that state symbol there. So the state symbol means solid. And so what that tells you is that you're making a precipitate. You've almost certainly done this reaction, so you probably know that it's yellow, but again, that's not actually in your spec. But so I would look at this reaction, I would see that in the products, I've got a solid. Over here, I don't have any solids, I just have solutions. And so because that solid is being formed, my solution is going to go cloudy. And what you usually do is you have a cross on a piece of paper, which you can see here, and you look at it from above and you see how long does it take until you can't see that cross anymore. This is a perfect opportunity for them to ask you about ways you could improve this experiment. So you could talk about the fact that humans are very subjective. Humans, you know, you're looking down and you're saying, oh, I think it's gone, oh no, I think I can still see it. So a better way to monitor this reaction would be to use a light sensor. And if you use a light sensor, then it can tell you when a particular amount of light is coming through or not coming through anymore. Someone's asking about writing PPT instead of precipitate. So what I would say is that your examiners are now not out to get you, your markers are not out to get you, and all of your markers, to mark science for AQA, you do have to have been teaching science for a couple of years, so it's extremely likely that they would know what you would mean, and it's extremely likely that they would say, yeah, I know what you're trying to say, and give you the mark. However, they don't have to. So I would err on the side of caution and write the full word, even though I reckon 90-95% of people probably would give you the mark for it, because they're not trying to deny you marks if you're writing good chemistry, but why would you take the chance? Have I been through the procedure? Yes, but you should be able to scroll back on the live stream. Also, if you want full written out methods, there was somebody on, I think it was the physics live stream, was asking about full written out methods. I think it was Aisha. So I did make a video for this this paper, which is all the chemistry required practicals for paper 2. There's a link in the description, and that does have for each one a full written out method, like a 6-mark question that you could just memorise. I have no idea why you're talking about percentage of sodium hydrogen carbonate concentration. I actually can't think of a reaction that does use that. Yeah. So for whatever reaction you're describing, you would need to talk about changing the concentration, and it's probably worth saying I would change the concentration by diluting it. You might even want to describe how you would do that, so sort of saying, oh, it'd have 2 centimetres cubed of acid and top it up with 8 of water, and then 4 centimetres cubed of acid and top it up with 6 of water, or whatever. That is your... Oh, right, I see what you mean. Okay, so, yes, concentration you are supposed to know in moles per decimetre cubed. Biologists quite often use percentages, chemists not so much. You use whatever the exam board has told you to use. So if they haven't specified, stick with moles per decimetre cubed, because that's what you know and love. But if they say to you, I don't know, I'm giving you a 10% solution of starch, then you can work with 10%. Right, reversible reactions. So in some chemical reactions, it's possible for the products to react together to make the original reactants, and we call those reversible reactions. And you can recognise them because of this here arrow. So make sure that you recognise it, make sure that you can draw it, because they have asked before for a little 1-mark question for you to draw that. And it's possible to change the direction of the reversible reaction by changing the reaction conditions. You should know that if a reversible reaction is exothermic in one direction, then it will be endothermic in the opposite direction. So there is a named example of this, and nobody knows this, nobody realises it's there, but this one here is in the spec. They could literally say to you, what colour is hydrated copper sulfate, and you are supposed to know that it is blue. So if you take some hydrated copper sulfate, which is the blue crystals that most of you would have made for the first required practical in paper 1, and you heat those up, you can make a white powder called anhydrous copper sulfate. It's the same thing that some of you might have made by accident in this practical if you heated your crystals for too long. And then if you take that anhydrous copper sulfate and you add some water to it, then you can turn it back into copper sulfate, hydrated copper sulfate, the blue one. And if you do that, it's an exothermic process. So if you take those boring white powder that you've made by accident and you add a little bit of water, then the test tube will get hot in your hand because it's an exothermic reaction. Ooh, went too far. So when a reversible reaction happens in a closed system, so in other words, in a closed container, no matter can get in or out, no energy can get in or out, then eventually it will reach a point called equilibrium. And this means that the forward and backward reactions are happening at the same rate or the same speed. So both the reactions are happening at the same time. This means that the concentration of the reactants and the products will not change. Now it's really, really important that does not say they are the same as each other, because they are not the same as each other. Don't get confused with your biology diffusion equilibrium. There is an entire multi-billion-dollar chemical industry that is totally focused on how to make there be as much product as possible and as little reactant as possible. So they are not the same as each other. Okay, so where we've got that reversible reaction going on, you could be asked, say, on a graph to indicate where it's reached equilibrium. So I've done a little arrow here. So the point is where my concentrations stop changing. This is now basically flat, it's a plateau. That's the point where it's reached equilibrium. Okay, so this is our first bit, which is just for higher tier. So it is combined science, you need it for combined science, but if you're taking the foundation tier papers, you don't need this bit. So if we've got a system that is at equilibrium and we try to change the reaction conditions, so it's no longer a closed system, then the system will respond to counteract the change. And this is called the Chatelier's principle. So for instance, if you add a reactant, the system will remove that reactant. And if you heat up the reaction, then the system will try to cool it down. but there are only two things that it can do to do this. It can favour, which means speed up the forward reaction, or it can favour the backward reaction or the reverse reaction. Those are the only two things it can do. The difference between equilibrium and dynamic equilibrium is that dynamic is taking into account, it's making it clearer that both reactions are happening. So really all equilibrium is dynamic equilibrium. It's just a nicer phrase for it, and it's one that we use a lot more at A level, because you're getting that point across that reactants are turning into products and products are turning back into reactants. And for the person who asked about the graph, no, so this is our concentration of the chemical. So this would be for the reaction A plus B turning into C plus D. So at the start, I've got lots of A and B and they get used up, and I've got no C and D, and I make some, and eventually we get to the point where those concentrations are unchanging. Okay, so let's look at some of these. So first thing, what will happen if I add more hydrochloric acid? So I need to have it in my head, whatever I try to do, the Chatelier's principle tells me the system is going to shift to counteract that change. It's going to be my nemesis. It's going to try and undo whatever I've done. So it's going to do whatever will remove hydrochloric acid. And I've only got two options. Either this forward reaction is going to happen more, or this reverse reaction is going to happen more. So if I've added more hydrochloric acid, it needs to use up the hydrochloric acid, which is going to be the forward reaction. So I would say the system shifts to remove hydrochloric acid, right? That's your first easy mark for any kind of equilibrium Le Chatelier principle question. You're going to say the system will shift to, and then basically undo whatever they said you're going to do. So the forward reaction is favoured, that means it goes faster. So the equilibrium shifts to the right. So my forward arrow points right, therefore equilibrium shifts right. So therefore I'm going to make more of this green copper compound. Okay, and you will really commonly find for equilibrium questions that rather than naming compounds or naming chemicals, the exam board quite often just say a blue copper compound, a pink cobalt compound, because they don't want you freaking out because you haven't heard of the chemical before. And equilibrium chemistry is quite complicated. So don't be confused if they just don't actually tell you what the chemical is. Okay, so next up we need to talk about pressure. So it's important that we understand what pressure is actually caused by. So pressure is caused by particles colliding with the walls of the container they're in. So if I've got twice as many particles, like I have on the right hand side, then there is twice as high a pressure. So if we increase the pressure, it will favour the side that has fewer molecules on it. So whereas with adding or taking away a reactant, we can just we can just say, oh, if I'm adding a reactant, it will always push right. Here, we're going to need to look at our simple equation. So here you can see I've got 3 moles of gas on the left and 2 moles of gas on the right. So you can see I'm using those coefficients there, right? They're important. And I should say pressure is only going to affect the position of equilibrium if we've got gases, because if we've got solids, they're just going to sit there, they're not colliding with anything. So first thing, if I decrease the pressure, Le Chatelier's principle tells me the system will shift to increase the pressure, and we increase the pressure by adding particles, and the reaction that's going to add particles is this reverse one here. So the system shifts to increase the pressure, the backward reaction is favoured, which means it goes faster. Because there are more molecules on the left, I counted them, so the equilibrium shifts to the left, so the yield, in other words, how much I make of sulfur trioxide is lower. Now, you might also encounter one where they could give you a reaction like this, and if they're feeling really mean, ask you what happens when you change the pressure. If they're not feeling so mean, they could say to you, why does changing the pressure not affect the position of this equilibrium? And the reason is that if I count up all of those gas particles, I've got 2 over here, and I've got 2 over here. So I've got the same number of moles of gas on both sides of the equation, therefore changing pressure is going to have no effect. Okay, so then we move on to temperature, and this is probably the most confusing one. So we said at the start that if we heat up a reaction at equilibrium, the system will shift to try to cool it back down again. And the way it does that is by favouring the endothermic reaction. So if I heat this reaction, then it's going to favour this one. But the reason this is a little bit harder is that very often they are not going to tell you both bits here. So very often what they'll do is not tell you that. They'll just tell you the reverse reaction is exothermic. So then you need to not just look for the endothermic reaction, but also know that if the reverse reaction is exothermic, the forward reaction is going to be endothermic. So we'd say that the system shifts to reduce the temperature, so the forward reaction is favoured because it's endothermic, so the equilibrium shifts to the right, so the mixture turns white. Depending on, someone's just asked in the comments about, could you say something about the yield being higher or lower? It depends on the structure of the question. So sometimes they will ask you specifically for an observation, in other words, something you can see. So then you would need to be mentioning, say it's going to be a colour change basically. If they just say to you, what's the result, then yes, you absolutely could say the yield would increase, the yield would decrease, whatever it is. And then the last thing is what will happen if we add a catalyst, and the answer is absolutely nothing. So catalysts speed up the rate of reaction, but they speed up the forward reaction and the reverse reaction by the same amount. So if you imagine a catalyst being like a special chemical that grabs the reactants and puts them together in the right order, well, in that case, they're also in the right order to switch back the other way. So adding a catalyst is not going to have any impact on the rate of, it's going to have an impact on the rate. It's not going to have any impact on the position of equilibrium. Right, quick drink. Okay, there's a question about saying, I don't understand how it shifts left or right, so let's see if I can make this clear one more time. Let's go back to this one, because it's probably easiest. So, if you're saying that you don't know, like you can't get your head around physically what's happening, don't worry, you don't need to. But basically, if you imagine, in each of my reactions, here's my blue copper compound and here's my hydrochloric acid, right? This is a terrible picture, but just roll with it. So, in order for them to react, they have to meet each other, they have to collide with each other. If I suddenly add a load more hydrochloric acid into that reaction, then it's suddenly really likely that this particle here is going to collide with one of them, because there's a bunch more of them just hanging around waiting to be collided with. If you're saying you don't get how you're supposed to know which reaction is which, start from the point of view of you're trying to undo whatever has happened. So here we've added hydrochloric acid, so you're trying to remove it. And then look at your you've basically got two reactions in a reversible reaction. So here we've got the blue copper compound and hydrochloric acid reacting to make green copper compound and water, and we've got the green copper compound and water reacting to make the blue copper compound and hydrochloric acid. So if we're trying to get rid of hydrochloric acid, it's got to be the reaction that takes hydrochloric acid and turns it into something else. Hopefully that makes a bit more sense. Okay, where do we get to? We got to here. Right, okay, so we're on to the second topic, which is organic chemistry. So this starts off talking all about crude oil. So crude oil is an unrefined fossil fuel. It's a finite resource, so we are using it up faster than it's being produced, and one day, quite soon, it will run out. It's found in deposits deep underground, trapped in rocks, and released by drilling. Crude oil was formed from the remains of ancient biomass, in other words, plankton. So millions of years ago, as those plankton died and they sank to the bottom of the ocean, they were covered in sediment which later hardened to rock, and under heat and pressure, their bodies transformed into the three fossil fuels, coal, oil, and gas. So the coal is formed from the remains of plants and phytoplankton, which are plankton that are kind of like plants, they're photosynthetic, and then the oil and the gas were formed from the zooplankton, from the animal plankton. Crude oil is a mixture of molecules called hydrocarbons, mainly of a class called alkanes, and hydrocarbons are compounds that contain hydrogen and carbon only, with no other elements present, so we need to get that only in there. So, based on that definition of a hydrocarbon, you should be able to identify which ones of these are hydrocarbons and explain why that's the case. So, if we look at the first one, we would say, oh no, that's not a hydrocarbon because it's got something in it that isn't hydrogen or carbon. No, you definitely don't need to know the binomial name of plankton, especially not for a chemistry exam. My goodness, how evil do you think they are? Second one, also not a hydrocarbon because it doesn't have any carbon in it. It's not a compound. Third one, still not a hydrocarbon because it's not a compound. We've got carbon, we've got hydrogen, but they're not bonded together. And then lastly, yes, we do have a hydrocarbon because this is a compound that only contains carbon and hydrogen, and of course it's methane. Okay, so we can split the hydrocarbons into some different types based on their chemistry, and methane is the first example of the alkanes. And alkanes are a homologous series. So this is a group of chemicals that have similar chemical properties because they have the same chemistry, basically. So they react in the same way. And the reason for that is that they have the same functional group and the same general formula, which we'll get to in a second. So sometimes we describe alkanes as being saturated hydrocarbons. Yes, this is still foundation. So the header is where it says Unit 7 Organic Chemistry. If it gets to higher, it changes colour and it says higher. If it doesn't say anything, it's foundation. Okay, so saturated hydrocarbons. So the molecule on the left is saturated because every atom is making the maximum number of single bonds to different atoms. Different is crucial. The molecule on the right is unsaturated. Oh no, what just happened? Ah! Right, hang on. I pressed a button. Come back, alkanes. Sorry guys, I hit end by accident and it just jumped on. Right, I did all that. There we go. Right, sorry about that. Okay, so one on the left is saturated because every carbon is making the maximum number of bonds. One on the right is unsaturated because these two carbon in the middle, instead of being bonded to the maximum number of different things, they've got 1, 2, 3 bonds. Oh, that was really unhelpful. I shouldn't have done that in the same colour. 1, 2, 3 bonds, and then it's got this double bond to the other carbon, and so we describe it as unsaturated. You need to be able to name and draw at least the first 4 alkanes, so hopefully you're quite familiar with those. And you might have encountered, I use most elephants prefer bacon to remember their names. So most elephants prefer, I like the PR for prefer, and then bacon, and that's my way of remembering things. You might have lots of other people, lots of other different ways of remembering it, whatever works for you, frankly. You also need to be able to give a formula for each one of them, and also a general formula. So if we look here at the central bit, you can see that for every carbon, there's a hydrogen above and below. So if we call the number of carbons N, then the number of hydrogens is going to be 2N. And then we've also got these 2 hydrogens that are on the ends. So our general formula for alkanes is CnH2n plus 2. So we could use that to figure out the formula of any alkane. So say we could say, oh, what if we've got 51 carbons? Okay, so in that case, the hydrogens is going to be 2 lots of 51 plus 2 on the end, so that'll be 102, so that'll be 104. And you can obviously do that in both directions. Hey, some people putting the answer in the chat already. Good job. Okay, so we said that crude oil is a mixture, important, they like putting that one in as little one marker, little multiple choice, a mixture of hydrocarbons, but all of those different compounds have different uses. So we've got fuels, which are chemicals that are burnt in oxygen to release energy, and then feedstocks, which are the raw materials used in industrial processes to make solvents and lubricants and detergents and polymers. But they all have different properties, and we can't use them for any of those things if we don't separate them out to just have a fraction that just has things with the same property in. So that brings us on to fractional distillation. So this is a process that we can use to split up all of those different compounds into not pure molecules, but fractions. So a fraction is a group of compounds that have similar boiling points. And when we're talking about mainly a mixture of alkanes, that's going to mean molecules that have similar chain lengths. So things like petrol has got chain lengths maybe sort of from about hexane up to decane, but something like diesel would have much longer carbon chains in there. Oh, okay. So when you put your fractions into this fractionating column, we're going to start off, we're going to heat them up to about 350 degrees C. Now it's really important, you're heating them, you're not burning them, because ultimately the aim of this is that your you're going to produce, say, some petrol that someone else can then put in their car, and then they're going to burn it. So you cannot start off by burning it. You can start off by heating it though. So we're going to heat that off when the crude oil goes in, and the vast majority of hydrocarbons are going to evaporate, and they're going to rise up that column. You will have some bitumen or some residue at the bottom because it's got such a high boiling point, it stays as a liquid, and that's what can be used to go on and make sort of tarmac and things. So up our fractionating column, we've got a temperature gradient, or you could just say it's hot at the bottom and cold at the top. But obviously, if you can remember the phrase temperature gradient, saves you a little bit of time. So as these hydrocarbons move up to where it's much, much cooler, they're going to start cooling down and condensing. And because they have different boiling points, they're going to condense in different places. So we know from paper 1 that where you have small molecules, they are held together by weak intermolecular forces, and that's what's being overcome when a small molecule, or a small molecular substance I should say, boils, right? We're not breaking any covalent bonds, never ever, but because these molecules have different sizes, they have weaker or stronger weak intermolecular forces. So the boiling point of methane is about minus 162 because it's got very, very weak intermolecular forces, whereas butane, it's still pretty low, but it's a lot higher than the methane because it's got 4 times as many weak intermolecular forces. This is not triple, and no, you don't need to memorise exact fractions anymore, although you are supposed to know a few of the names of them, just like petrol and diesel and naphtha, but not the whole shebang, and not anything about what order they're in. Okay, so the smaller molecules are going to end up condensing at the top of the column because they have the lowest boiling point. So the molecules are going to carry on rising up the column until they hit the point where their boiling point is. So maybe if you imagine like this is 300 and this is 250 and this is 200. I am just pulling these numbers out of the air, by the way, they're not like real numbers. But the point is, as it goes up, it gets cooler and cooler, and when each molecule reaches its particular boiling point, then it condenses. So the ones that are collected at the top of the column are smaller molecules. They've got the lowest boiling point. They've also got the lowest viscosity. So in other words, they're not very sticky. Golden syrup is very viscous. That's what viscosity means. And also they're extremely flammable. So they are the very best fuels because they're going to burn at the most cleanly. And that leads us nicely on to combustion. So combustion is the proper chemistry name for burning a fuel in oxygen. And based on the amount of oxygen that's available, that combustion can be described as either complete or incomplete. If there's a lot of oxygen available, then all of the fuel can be fully oxidised, and we call this complete combustion. And it's going to make carbon dioxide and water as the products. If there's insufficient oxygen available, then some of the fuel may not be fully oxidised, and instead of making carbon dioxide, it will make some carbon monoxide or carbon particulates, also known as soot. Note the names of the different fractions, definitely not in, like there were definitely some, though you can get exam questions that are from the old specification where you needed to know, but we threw that one out in 2018, so I wouldn't worry about it. Okay, so you do need to be able to balance combustion equations. Hopefully you can all balance equations fine, but combustion ones are more likely to come up than pretty much anything else. So even if you can't balance equations and it's a bit too late to learn, there is a little trick you can use for just the complete combustion of alkanes. So if we take some propane and say it's going to react with some oxygen and it's reacting completely, it will make carbon dioxide and water. So what I'm then going to do is, I know the law of conservation of mass tells me that the number of atoms of a particular type can't change. So I've got 3 carbons on the left, therefore I must have 3 carbons on the right. And when I'm balancing an equation, all I can do is add coefficients at the front. That's what this big number is called, it's coefficient. I can't change the formula of the compound. So I couldn't change that H2O to H2O2 because that would be hydrogen peroxide, and that's not what this reaction makes, it makes water. But what I can do is change the number of waters. So 3 carbons, 3 carbons, I've got 8 hydrogen. So because water has got 2 hydrogens in, that means I'm going to need 4 water. And then this is the tricky bit, I now need to add up all the oxygens I've got on the right, and then those 10 oxygens also have to be on the left, and I know I've got O2 molecules, so I'm going to need 5 of those. Now that works absolutely fine as long as I've got an alkane that has an odd number of carbons. If I've got an even number of carbons, then I can use the same method, but I will end up having to use halves in my coefficients, so like 4.5 oxygen or 6.5 oxygen. You can do that, it is now allowed at GCSE, but it tends to confuse people. So your alternative is, if you've got something like this butane here, which obviously does not have an odd number of carbons in it, you can start off by doubling it, and then we can still go through the same process. So I've now got 8 carbon in total on the left, so 8 carbon dioxides. I've got 20 hydrogen in total, so 10 waters, and then I'm going to count up all the ones that I've got, and I'm going to have 13 oxygen. So you can see there, if I hadn't doubled that butane, then I would end up with 6.5 moles of oxygen, which is just a little bit confusing. Okay, so you also need to know about some of the problems with using hydrocarbon fuels. So there are various pollutants that are released when fuels are burned. Remember, you can never just say a pollutant is released, a gas is released, something bad is released. You need to be naming things. So first up, obviously, carbon dioxide leads to global warming and all the bad stuff about that we'll talk about a bit more in Unit 9. If you don't have enough oxygen, then instead of making carbon dioxide, you make carbon monoxide or even carbon particulates. So carbon monoxide is a toxic odourless gas that stops your red blood cells from working properly. And carbon particulates can cause global dimming, which literally means the sky is getting darker and less light is getting to Earth. If they're wanting you to write an equation for propane, they would tell you that it needed to be propane, but they don't have to tell you what the formula of propane is, because Unit 7 is also in this paper, so you should know what the formula of propane is, because you should know that propane is the third alkane, and you should know the general formula so you can work out that it's C3H8. Almost all fossil fuels have got small amounts of sulfur in them as impurities, so when you burn the fossil fuels you also burn the sulfur and you make sulfur dioxide. And sulfur dioxide, along with carbon dioxide and nitrous oxides, are going to cause acid rain. Those oxides of nitrogen are produced inside combustion engines mainly. Nitrogen is very unreactive, but at super high temperatures it can and will react. So a combustion engine is one of the places that's going to happen, like in a car, but also lightning can make the same thing happen. Okay. So this graph shows the approximate percentages of different fractions present in crude oil, and also the approximate percentages of those fractions that we actually need. So as you can see, there's a greater demand for petrol and diesel than what we can supply with crude oil alone, while larger fractions like fuel oil are more available than necessary. So cracking is a process that allows this surplus of fuel oil and other large fractions to be converted into smaller, more useful molecules. So it's an example of thermal decomposition. Decomposition means breaking something down, and thermal decomposition is breaking it down using heat. Because conservation of matter is a thing, we know that the number and the type of atoms can't change. So when we break apart a large alkane, like this decane molecule, if we make another alkane, like this octane molecule, you can see I've got 10 carbons to start with and then 8 on the right hand side. So I've got 2 left over. And then 22 hydrogens and 18 on the right hand side. So I've got 4 left over. So that gives me C2H4, which is not an alkane, it's missing 2 oxygens. So instead, the products of cracking are going to be 1 alkane and then 1 or more alkene, which is what this small molecule here is. So alkanes, we've already talked about. Alkenes are unsaturated hydrocarbons, which means that they contain double bonds. So you need to be able to draw these just like you did for the alkanes. So we start off with a carbon-carbon chain, and then you're going to add in 1 double bond to that. So even if you've got a carbon chain that's 10 carbons long, you're only going to have 1 double bond in. Then you're going to add your hydrogens around, making sure that each carbon is only making 4 bonds in total. So a double bond counts as 2 bonds. So this one is ethene. So we name our alkenes in similar ways to our alkanes, except we use the suffix "ene" instead of "ane." So this is one of the words. There are very few words in GCSE Science where your spelling is going to matter, and where it's important that your marker can read your spelling, but this is one of them. So I quite often write alkane and alkene in capital letters to make it very, very clear which one I'm talking about. So this first alkene is ethene. There is no methane because it's not possible for one carbon atom to make a double bond with itself. So we've got ethene and then propene and then butene. So those are all the prefixes we've used before. And then our fourth one is pentene, which is nice and easy to remember because it's just pent, like a pentagon or a pentagram or something like that. And you can see that for all of those, there is only one double bond, okay? It's a really common mistake that you see people putting double bonds for every carbon, and that's not right. Alkenes are more reactive molecules than alkanes, and we can differentiate between the two types of molecules using a test called the bromine water test. Bromine water is to detect the presence of unsaturated bonds, so since that's the only difference between an alkane and an alkene, it allows us to work out which one's which. So, before it reacts with any other chemicals, bromine water is a transparent orange solution. And if you mix it with an alkane, then no reaction happens, so it stays orange. Whereas if you mix it with an unsaturated molecule, like an alkene, then it turns colourless. This word here, colourless, is super, super, super important. You absolutely cannot write clear. Clear will not get you any marks, and it's called out every single year by the examiners, because this one is already clear. This is clear, I can see through it. It just happens to be orange. So the word is colourless. Okay, so we've said that when we break down a larger molecule, we're going to make an alkane and an alkene. You might be given some symbol equations to balance. So there are two types. In one type, you're just given one reactant and one product. So we can just kind of go, right, we've got 25 carbons here, 10 here, so 25 take 10 is 15, and then we've got 52 hydrogens, 22 hydrogens, so 52 take 22 is 30. Okay, so in that case I'm going to have C15, H30. And then this is the more challenging one, where they tell you that we're making some ethene, but you need to figure out how much. So we're going to do basically the same thing here and say, right, C25 down to C9, so that's C16 in total, but I know this is in the form of ethene. So how many ethene molecules are going to contain 16 carbons? Oh, it's going to be 8. You could also do the same thing with the hydrogen. You could say that's decreased by 32, so how many would give me that H4 there? And again, it would be 8. You need to be able to describe the reaction conditions for two different types of cracking. So there's catalytic cracking, which involves a catalyst. Here's my large alkane that I'm going to crack, and there's my catalyst. So we've said that's a chemical that speeds up the rate of reaction without being used of itself. We're going to have a heat source because it's a type of thermal decomposition, and then those vapours are passed over the hot catalyst, and we're going to collect the gas so that we can then test it and prove whether it's an alkane or an alkene. So for catalytic cracking, we're going to vaporise that alkane with high temperature, and then we're going to pass it over that zeolite catalyst. The second type of cracking is steam cracking, which also requires a very high temperature, but it uses steam in place of a catalyst. And you'll notice that neither of those methods made any mention of high pressure, because in GCSE chemistry we do not talk about the role of pressure in cracking at all, and you won't get a mark if you mention it. Okay, more water time. Okay, so the next chunk of stuff is for the triple scientists. So if you are taking combined science, you've probably got about maybe as much as 10 minutes before there's going to be anything more for you. So if you're in need of a snack, now is the time to go get your snack on. Okay, triple only content, you can tell because it's gone green at the top and it says triple chemistry only. So one of the things that alkenes are really useful for is making polymers. So you know all about polymers, we'll talk more about them in a second. However, there are some other reactions you need to know about as well. So we can react them with hydrogen in order to turn them back into alkanes. And you should know that for that, you're going to use a nickel catalyst. We can also react them with water to make alcohols. using an acid catalyst. You don't need to know which acid, any acid will do. And about 300 degrees C and about, what's that doing? And about 60 atmospheres, which is the pressure. And also we can burn them, which they do burn, but they produce quite a smoky flame. So in other words, they're more likely to undergo incomplete combustion, and they're just not very good fuels. They're not very useful fuels. So we tend not to use them as fuels because there are other things that we could use that would be better. Okay, so our next group, our next homologous series are the alcohols. So these are defined by their functional group, which is a hydroxy group, or you can just call it an OH group. It's definitely not a hydroxide group, right? Hydroxide is the name of the ion, so that's a charged particle that can break off and be out in solution, which is not what this is. The general formula for alcohols is going to be CnH2n plus 1 OH. And, you know, just like with any other general formula, you can use that to work out the molecular formula of a specific alcohol. And we're going to name them in a very similar way to how we have the others. So the same prefixes, but this time our ending is going to be anol, like ethanol or propanol. So you should be able to draw them all. So basically what you're going to do is draw an alkane, and then at the very last minute, instead of putting your final H on, you're going to put OH instead. So we have methanol, ethanol, propanol, butanol. In addition to being the sort of active ingredient in alcoholic beverages like beer and wine, ethanol and other alcohols are used as solvents, so they're used to dissolve things, and as fuels, so you can burn them, and also as some feedstocks. There are two main ways that we can make ethanol. So this one is going to work for all alcohols, but this one is just for ethanol. So we can do fermentation. So this is anaerobic respiration by yeast. So you give them some sugar, you put them somewhere that is warm, not super hot. If you get above about 40 degrees, your yeast will all die. So warm, wet, and crucially anaerobic. If the yeast have oxygen, they will just do normal aerobic respiration and all your sugar will just be turned into carbon dioxide. Whereas if you don't give them enough oxygen, then they will do fermentation instead. That produces alcohol very cheaply, but also very slowly. And also it's going to be very impure. So you're then going to need to distill it if you want to use it for anything other than just drinking it. Whereas hydrating our alkenes with some steam, that is a way that we can produce any alcohol that we want. It's more expensive because we've got to heat it up to a high temperature and make the steam and so on. But also it's going to give us much, much purer alcohol. So particularly if you want it for doing some chemistry with, or doing like some DNA sequencing in biology, then that's the alcohol that you're going to want. Other things you should know: alcohols dissolve in water to make neutral solutions. Once again, this is a hydroxy group or hydroxyl group. It's not a hydroxide ion, so it's not going to affect the pH. So this is just a neutral compound. Alcohols burn to produce carbon dioxide and water, and in fact they're really good fuels because they're basically an alkane with some extra oxygen added. So they can burn cleanly in slightly less oxygen than an alkane can. You can also react them with sodium, which will release some hydrogen, and you can test that with a squeaky pop test. To the people complaining about my drinking water, can you hear how hoarse I'm getting? I've been talking consistently for an hour. Give me a break. Also, we can oxidise these alcohols either by microbes, so just like bacteria and things in the air, or chemical oxidising agents, so that could be things like potassium permanganate is my personal favourite, and that is how we make carboxylic acids, which are our next homologous series. Sorry, completely forgot the word for a second there. Okay, so our first four members are methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. So named because it's what you find in rancid butter. No, I am not joking, that's literally where the but in butane and so on comes from. They dissolve in water to form weak acids. So in other words, they don't fully ionise, we should probably say in aqueous solution, shouldn't we? Because we want to get all the marks if that was to come up. And so they have higher pHs compared to, say, hydrochloric acid or nitric acid, which are strong acids. at the same concentration. They are acids though, so they will react with carbonates to produce carbon dioxide gas bubbles, so we could test them with lime water. We'll talk about that in the next topic. And they also react with alcohols to make esters. So esters are sweet smelling volatile substances. So volatile means they evaporate easily, and so they're very often used as perfumes and flavourings because they're good for that. Their functional group is this carbon double bonded to one oxygen and then single bonded to another oxygen. If you can't remember which way round they go, think about the fact that every element has a certain number of bonds it likes to make. And so this oxygen here and this oxygen here are going to make the same number of bonds. So if you draw it the right way around, then I've got 2 bonds here and 2 bonds here. If I drew it the wrong way around with a single bond up there and then the double bond down here, then this one would be making 3 bonds and this one would only be making 1. So that's a useful way of remembering it. So this is called a condensation reaction, and in that condensation reaction, water is lost. So the hydrogen from the carboxylic acid and the hydroxy from the alcohol are going to join up together, and they're going to make, that's going to be water, and that water is going to be lost. And then we have this bond forming here. And actually, I don't know why I've used that one as an example. There is only one example of an ester that you are supposed to know the name of, and it's not the one I've drawn, it's this one, ethyl ethanoate. Okay, so then we get on to polymers. Now, obviously you have had polymers already as part of Unit 2, but there is quite a bit of triple content about polymers, which comes up in Paper 2. Both in Unit 7 and also in Unit 10. So you know from Unit 2 it's a very long chain of repeating units. You know that the word very is really important. You know that those repeating units are called monomers, and you know that there are strong covalent bonds inside each polymer thread and then weak intermolecular forces between them. So new stuff for Unit 7. Addition polymers and condensation polymers. So an addition polymer is made from monomers that have a double bond in the middle. And that double bond is going to break, and that's going to allow each one of the carbon atoms to form a new bond. And so therefore it can bond to a monomer on either side, and we get our very, very long chain. Really important that you can recognise these diagrams and also you can draw them. So at the start of the reaction, the N... Oh, my thing's gone totally where I didn't expect it to. At the start of the reaction, the N goes at the start. At the end of the reaction, the N goes at the end. That's how you remember them being which way around they are. Also, when we start off with our monomer, we've got our double bond, but in our polymer, we only have single bonds. Also, in our polymer, we have our bonds going out the side, and also we've got our brackets, right? So you should know all of them. And of course, you do still need to be able to name polymers from their monomers. So if we start off with chloropropene, we finish up with polychloropropene. Then we have condensation polymerization, a lot like that condensation reaction that we just had with our ester. So for a condensation polymerization reaction, you need 2 functional groups. Now that could either be 2 different monomers that have a functional group at both ends. So basically you can have an alcohol that has an alcohol group at both ends, and you can have a carboxylic acid that has a carboxylic acid group at both ends, like that. Or you can have a situation like this. This is an amino acid called glycine, and this has got an amine group at one end and a carboxylic acid group at the other end. So as long as we've got 2 functional groups, either one works. And so just like we had with making the ester, we're going to lose a water molecule and be left with the rest of our polymer. So if you're trying to figure out whether something is an addition polymer or a condensation polymer, the trick is, are all the atoms you started with in the polymer? If they are, it's an addition polymer. If they're not, it's condensation polymer. Yes, you do need to know how to draw the ester because it is in your spec. Oh no. Oh, I forgot that I'd drawn on this one. Hold on. Discard those. Right, there we go. So there's an example of how that condensation polymerization would work. Okay, you've got some named examples of natural polymers. So you should know about DNA. It's not just for biology. You need to know it has a double helix structure. You need to know that it's made from 2 polymer chains. And you need to know that those polymer chains are made from 4 complementary nucleotides, not 4 complementary bases. So the bases are just the bit in the middle of the nucleotide that give us the sequence. The nucleotide is the whole thing, including the sugar phosphate backbone. So the monomer for DNA is nucleotides, not bases. And you obviously know that adenine bonds with thymine and cytosine bonds with guanine. Then we've got proteins, which are made from amino acids. This picture of glycine that I just drew is in your spec. I can't remember if it says it's glycine or not, but it says amino acids like this. So practice drawing that one if you're not familiar with it. And then starch is a polymer made from glucose. Okay, so next up we've got Unit 8. If you're doing combined science, you're back in the room, we're ready for you. Come back and join us. Okay, so for Unit 8, you need to know 2 different definitions of the word pure, which is really annoying because you need to know both of them. So in your ordinary everyday life, if you were to talk about something as being pure, maybe some pure orange juice, you would mean nothing's been added to it, nothing's been changed about it. We might describe it as unadulterated. So this very simplified picture here shows you that within some orange juice, we've got some water molecules, but we've also got some sugar molecules, and those sugar molecules came from the orange. I haven't added them in. So this is pure orange juice, even though it's got different things in it. And then in contrast to that, in chemistry, when we describe a substance as pure, we mean it hasn't been mixed with any other substance. So the next part is all about separating mixtures, and this can be done with physical processes like heating or cooling or filtering. They're going to split up the different parts of the mixture without changing any of the chemicals. So this mixture contains nitrogen with its triple bonds, the hydrogen and the ammonia, which is the NH3. Those 3 molecules have different boiling points, and that means that by controlling the temperature of the mixture, we can ensure that the ammonia is a liquid while the hydrogen and nitrogen are still gases, and that allows us to separate them out. Okay, so we've got some different ways that we can separate them, and we mentioned these also in Unit 1, but they're still relevant here. So we've got filtration, which is how we separate an insoluble solid from a liquid by passing it through filter paper. We've got crystallization, which is where we gently heat a solution that contains a soluble solid so that the solvent evaporates and the soluble solid is left behind. We've then got simple distillation and fractional distillation, which is separating things according to their boiling points. And then finally, we've got chromatography, which is an analytical technique where we separate out mixtures of liquids based on how attracted they are to the mobile phase and the stationary phase. But we'll go through that in quite a lot of detail because that is a required practical. So in addition to separating out mixtures into pure elements and compounds, we need to be able to prove that a substance is pure. So this is going to come back in Unit 10 when we think about the water required practical. One way we can do this is by looking at the melting or boiling point, because pure substances have a single unchanging melting and boiling point, which you can look up in a data book. So for instance, we know that pure water boils at exactly 100. So if a sample does not boil at 100, then it's not pure. So GCSE physics, you've met melting and heating curves, so you know that we sort of have this situation where the temperature rises, and then when you get to a state change the temperature stops rising, and then the temperature rises a bit more. When you get to your next state change the temperature stops rising, and you have these really sharp horizontal bits. Whereas if you've got an impure substance, then you get something that's a bit more weird and wonky, and it doesn't flatten out completely, just the gradient gets a bit shallower. So if you're looking at one like that, you know that you're thinking about an impure substance. Next thing, a formulation is a mixture that has been designed as a useful product, and we make them by mixing the components in carefully measured quantities to ensure that the product has the required properties. And there's a whole bunch of examples that are named in your spec. So fuels, so that's kind of getting back to Unit 7 and organic chemistry, cleaning agents, paints, medicines, alloys, fertilisers and foods. So, bit of a reminder about alloys, which you did cover in Unit 2, but they're still here. We could talk about the fact that in a pure metal, the ions are all one size. We can't say particles. We could say atoms, we'll let you have atoms, but we can't say particles because the electrons are small. So even in a pure metal, you have particles of different sizes, but you don't have ions of different sizes. So they're all one size, they're all in regular rows, and therefore they can slide over each other. Whereas in an alloy, we've got different sizes, so the rows are distorted, so they can't slide, and that makes it less malleable. Oh, there's my sliding atoms. Okay, so chromatography. So this is, the required practical is in this bit, but there is also some information you need to know that's not to do with the required practical. So, one way that we can identify whether a substance is pure and which different substances it contains if it's not pure is by using chromatography. There are quite a few different types of chromatography, but the only one you need to know details of for the GCSE is paper chromatography. That doesn't mean that they can't say, oh, here, we're going to give you a load of information about a type of chromatography you've never heard of, and then ask you to answer questions about it. And one thing that I know we have found in the 2025 exam series, both for GCSE and A-level, is that this year, for some reason, we're seeing a lot more novel context AO3 questions. So, you know, this is an example of one place that they could give you some information and ask you to work things out. So, all types of chromatography are used to separate out mixtures, and they're all used to analyse what's in them. So this isn't like fractional distillation where we're just trying to split up the different bits. We want to know what's there. All types of chromatography, regardless of which one it is, have a stationary phase, which is going to stay still, and a mobile phase, which is going to move. And the results that we get are based on retention. So it's based on the attraction to the stationary phase and the attraction to the mobile phase. So if a substance is really attracted to the stationary phase, it will stay quite low down. If it's really attracted to the mobile phase, it will move quite far. And when we're thinking about paper chromatography, this is linked to solubility. So if a substance is very soluble, it's very attracted to the solvent, which is the mobile phase. If it's very insoluble, then it's very attracted to the stationary phase, which is the paper. So, required practical. You should have set up and analysed a paper chromatogram. Usually it's something like examining a few different types of felt pen to see whether they have the same mixture of inks. So there are a few key points that you need to know. First up, we've got this start line here where we're trying to make sure that everything is starting at the same height. And it's oh goodness, why do I keep pressing that button? It's really important that it's in pencil, because if it was in pen, then the pen would run and we wouldn't know what was our sample and what was the pen from the start line. Likewise, our solvent, which is here, which was probably water when you did it, but it could be other liquids, it could be ethanol, it could be methanol, that needs to be below the start line, right? You can't have it coming over the start line, because if you did, then all your samples would just leach out into that liquid. They wouldn't be pulled up the paper by the capillary action. Also, if you're using a volatile solvent, so something like methanol or ethanol, then it's really important that we've got a lid on it to stop it from evaporating. And then, depending on the type of chromatography we're doing, we're either going to have some known chemicals, which are our standards, so we know what these are, and then we're going to compare our sample to those and say, is it the same as A? Is it the same as B? Or we can calculate an RF value, and we can do that quantitatively instead. So, the results that you did when you actually did this experiment probably looked a little bit like this, but in real life, you're going to, in your exam, you're going to be given something that's a bit more like this. So we can examine these and we can draw conclusions that are qualitative or quantitative. So qualitative is no numbers, right? It's just kind of what's the same, what's different. So we know that a pure element or a pure compound will produce a single spot in all solvents. So the fact that my sample here has not got a single spot, it's got 3 of them, that tells me it's not pure. But my standards could well be. So the first thing I could say, looking at this, is that because my sample has got 3 spots, that means it contains 3 different colours. Now, one thing I should say is that for paper chromatography that you do in school, you're almost always examining colours. So it's really likely in the exam that they say to you, how many different colours are in the sample? Your exam paper is printed in black and white, and there is always a few people who are going, how was I supposed to know how many different colours there are? Because it's in black and white. So when they say how many different colours, they mean how many spots are there. And then this is a comparative technique, right? It's like fingerprinting. So we can't just look at a spot and say, oh, that's arsenic. What we would need is some arsenic as one of our standards that we can then compare it to and say, oh, this is at the same height. So we can say that my sample contains A because we've got this spot here that is at the same height as the A one. And it contains B because it's got this spot here that is at the same height as B. And then this third one, well, we don't actually know what that is because it doesn't match any of our standards. But we know there is a third one, we just don't know what that third one is. Anything else we need to say? Oh yes, so this one here, this is something that is insoluble, or you could say it's something that is very attracted to the stationary phase and not very attracted to the mobile phase. Okay, so then we get to our quantitative conclusions. So this is our using our numbers, calculating our RF values. And this is useful to do because if I'm going to put my standards on every single chromatogram I do, that's fine if you're just doing it once in school. But if you imagine this is happening in industry, they're trying to figure out what's going on with forensics or whatever, it would get really time consuming and really costly and really wasteful to put those standards on every time. So instead, an RF value allows you to just have a number that can tell you does it match this sample or not. So the way that we're going to calculate it is the distance moved by the substance divided by the distance moved by the solvent. So you could have a situation where you actually have to measure this yourself, get your ruler out and everything. And it's going to give you a value that is between 0 and 1. I have no idea why it says S after it. Let's just cross that out. So if it's 0, it's going to be something like this, where it hasn't moved at all. If it's 1, it will be something that it has moved as far as the solvent front up here. Okay, so if you get a value that's not between 0 and 1, then you've done it wrong. And because that RF value is caused by the attraction of the substance to the stationary phase and the mobile phase, if you change the mobile phase, so if you do it with a different solvent, you will get a different RF value. And so actually, if we want to say conclusively that this is A, then we need to do this in a few different solvents and say, is it always the same height as A? Does it always give the same RF value as A? So when you're doing these measurements, you want to measure it from the centre of the spot, from the start line, and then from the solvent front also to the start line, and that's what you're comparing. Also in this chemical analysis topic, we touch on the idea of instrumental methods versus human methods. So instrumental methods are accurate, in other words, they give you the right answer. They're rapid, so they're very fast, and they're sensitive. So that means that they can detect tiny, tiny amounts of whatever it is you're trying to detect. However, they tend to be more expensive because you're having to buy the instrument, buy the machine or the computer or whatever, and also they often need skilled technicians to do them. To run them. So that's adding another cost involved, and also you might not be able to find people who are willing to work for you for that. Yes, you do need to memorise the formula to find the RF value. Okay, so we're on to some gas tests. So first up we've got our oxygen, which will relight a glowing splint. So here's my splint, blow it out to make it glow, and then hold it in some gas, and as if by magic, eventually, there we go, it relights. Okay, so that demonstrates that the gas that is being produced in that reaction is in fact oxygen that's being produced. And then our second one is our hydrogen squeaky pop test. Definitely hydrogen. And then we've got our chlorine test. Now you need to be careful, particularly if you're doing triple science, because chlorine and chloride ions are not the same thing as each other. So if we're testing for chlorine, then we need damp litmus paper. In other words, it needs to be wet, and it doesn't matter what colour it is. I know there are some of the revision guides say it needs to be red or it needs to be blue. Literally does not matter. The reason it works is that when chlorine dissolves, it makes bleach, and so it will bleach it whatever colour it is, but it does have to be wet. And then our last test is to bubble a gas through lime water, which is aqueous calcium hydroxide, and if it goes cloudy, then that tells us that it's carbon dioxide. So you can see the bubbling there, and you can see that gradually it's going a bit milky, it's going a bit cloudy. This was some quite old lime water, so it didn't work very well, but you get the general vibe. Thermosetting and thermosoftening is chemistry, but not until Unit 10. So we'll get there eventually. Right. Unit 10 is the using resources topic. And no, the combined scientists don't need to know that bit, it's just the triple bit. Right. Okay, also flame testing. So we know that lots of different metals, if you burn them in a Bunsen burner flame, they give you a characteristic colour. I'll just skip over that bit. So this here, this crimson flame tells me that I had some lithium ions in there. Or this green flame here tells me that I had some copper ions here. So the process is that you clean off your wire, and then you dip the loop into some solid salt or into a salt solution, and then you hold it in the flame, and you see the colour change of the flame, and yeah, that allows you to identify what was in there. So, oh yeah, so I forgot to speed this video on a bit. So yeah, so that's an example of the green flame for the copper. So those are the colours of the ions that you need to know. Also, you need to be aware that this is not very good at detecting mixtures of ions. So potassium is really, really pale lilac. It's very hard to see anyway. If you have a sample that has some lithium as well as potassium, or some copper as well as potassium, you just won't see it. So that's where we then need to turn to our flame emission spectroscopy. So this is another example of an instrumental method, which is accurate, rapid and sensitive. So we put the sample in a flame, and rather than you just looking at the light and saying, oh, I think that's crimson coloured, it gets passed through a spectroscope, and this produces a line spectrum. So basically you get lines in different places that correspond to different wavelengths, and by comparing those you can identify what metals are present. Then we've got our hydroxide tests, so this can also be used for identifying cations. So first up, I've got copper. And if I add the sodium hydroxide... Let's just turn the sound off because I forgot there was sound on that one. So you can see here, for copper, we get a blue precipitate. And then for iron, you can see that dark green precipitate there. That's going to be iron 2+ ions. No combined scientists don't need to know the flame colours, that's why it was green at the top. This bit's triple only. And then iron 3+ is going to be that orangey brown. And then you've also got the white precipitates. So these are calcium and magnesium and aluminium. And crucially, if you keep on adding sodium hydroxide, then the aluminium will eventually redissolve. Okay, you could be asked to write some ionic equations for these. So basically, look at the charge on the iron, and that's how many hydroxides you need. So copper 2+ needs 2 hydroxides, iron 3+ needs 3 hydroxides. And then you're going to make your precipitates like this, so the number of hydroxides is the same as the number of hydroxides that you've added. And you would put those in brackets, and you obviously don't have any charges inside the formula for the final compound. Then we've got our sulfate test. We add hydrochloric acid to break down any carbonates that are in there, because they would give us a false positive. Then we add some barium chloride, and we get a white precipitate if we get a positive test. So we add some barium chloride, and my first tube here absolutely nothing happens, so there are no sulfate ions there. Whereas my second tube here, you can see that white precipitate forming. And obviously I know that looks kind of pale blue, but it's because the original solution was blue. So you could be asked to write symbol or ionic equations for that. So you should know the formula of barium chloride. You should know the formula, well, they would give you the formula of whatever you were adding it to. So there I was adding it to copper sulfate. And then you should know that this barium sulfate that's being made, that's that white precipitate, is BaSO4. And you would work out what the formula of the other compound was. You can identify, we talked before about the fact that because it's got an S in brackets, that's my state symbol, that tells me that, that's a precipitate, and that's a white precipitate. Or we could just write an ionic equation for it as well.
So for this next test, I'm testing for halide.
So then we've got our halide ion tests. So this one, we're going to add nitric acid, again to get rid of any carbonates, and then add some silver nitrate. And we get 3 precipitates that are white for chloride ions on the left, and then so we got chloride ions there, bromide ions, stop moving, bromide ions that are cream, and iodide ions that are yellow. So basically as you go down the table it gets more strongly coloured. So they have asked before for you to like make a prediction about what colour do you think astatine would be then, and you would probably say something like orange or brown. Yeah, so that's pretty much all for that. So again, they could ask you to write equations for those. In each instance you're just making the precipitate that you're seeing is a silver halide, and it's a precipitate, so it's got a solid state symbol after it. And if you add fluoride ions, you don't see anything at all because silver fluoride is soluble, so it doesn't make a precipitate, so you can't see it. And then we've got our bubbling gas through lime water, which actually, to be honest, we already looked at. So we gradually get that white precipitate forming. So just to look at this one quickly, the bit you need is this bit down here. Sorry, I've cut this out of another presentation and given you more than you need. So aqueous calcium hydroxide, that is lime water. And then when you add the carbon dioxide, you get calcium carbonate and also some water being made. Speaking of which, right, on to Unit 9. We've got 2 topics left to go. So, the Earth's atmosphere today starts off with about 80% nitrogen and about 20% oxygen. Now, when we say modern, we're using that term fairly loosely because for about the last 200 million years, the Earth's atmosphere has been pretty much constant. If you know more accurate numbers than 80%, 20%, that's fine, but those are the numbers from your spec. So in addition to those, there are small proportions of other gases. There's a tiny amount of carbon dioxide and also variable amounts of water vapour, depending on things like how close do you live to the coast or to rivers or lakes or things. And some noble gases, so in other words, things like argon. It's really important when you're talking about the water vapour, particularly when we get to the greenhouse gas bit, that you are using the word vapour, because if it's not water vapour, it's not a gas. So that's important. Now, a word of advice, a bit of exam technique, it is incredibly likely that you are asked to compare the atmosphere of the Earth at some point to some point. And pretty much every year there's a question that is either early versus modern, or it's just asking you about the last 200 years. And always about half the students don't read the question and start talking about the other one. So just make sure you know, are they asking you about 4.6 billion years ago? Or are they asking you about 200 years ago? So, early atmosphere. We're talking 4.6 billion years ago when the Earth's atmosphere first formed, and there is limited evidence. So sometimes they ask you, why can't we say exactly what it's like? And the answer is there is limited evidence. Please don't say nobody was there. Because nobody was there 65 million years ago when the dinosaurs went extinct, but we've got a pretty good idea of what happened at that point because we can look at rocks from the time, we can see all these iridium deposits, we can see ice cores, there's all this evidence that we can use. So it doesn't matter that there were no humans alive, what matters is that we don't have sufficient evidence. So over the time, as science has moved on, we've learnt new things, we've gathered more evidence, and so sometimes our theories have needed to change to accommodate that. Because what we do as scientists is we do experiments, we collect data, and we've updated our theories. So the best evidence that we've got says that for about the first 1 billion years of the Earth's history, the whole surface was covered in volcanoes. And as you know, volcanoes are spewing out rock that is so hot, it's turned into a liquid, what we call lava, or magma if it's still inside the volcano. So if you think about how hot that must have been, it makes complete sense that for the first billion years, there weren't any oceans on Earth, because any water that was present would just turn into a gas and it would boil off. So in addition to spewing out molten rock, those volcanoes would have been giving out a selection of gases that formed the Earth's early atmosphere. And we currently believe that Earth's early atmosphere was most similar to the atmospheres that we see today on Mars and Venus. So if you look at Mars and Venus today, they have still got loads and loads and loads of carbon dioxide. That's the main thing. The difference is that they have varying amounts of the sort of the trace gases. So like potentially a little bit of nitrogen, potentially a little bit of oxygen. You don't really need to know the makeup as long as you know they had shed loads of carbon dioxide. And anything more than that, you're going to be given data to compare. But anyway, back to life on Earth. So the volcanoes were giving out loads and loads of carbon dioxide and then smaller amounts of water and nitrogen and ammonia and methane. So as Earth aged, that volcanic activity started to die down, and with it the temperature on Earth began to drop, and eventually it dropped low enough that all the water vapour that had been in the Earth's atmosphere was able to condense into liquid water, and suddenly we had the Earth's first oceans. Now that's important for two reasons. The first reason is that the carbon dioxide that was in the atmosphere was able to dissolve in those oceans, forming chemical compounds called carbonates. And those carbonates precipitated out, which means they became insoluble solids and they were able to drop to the bottom of the ocean. So this is where we get lots of our sedimentary rocks from that contain carbonates. And the second thing is that 2.7 billion years ago, algae started using that dissolved carbon dioxide for photosynthesis. Now note, it says algae, it doesn't say plants. Plants came quite a bit later, and it's important that you do understand that. So the carbon dioxide dissolving and the algae doing photosynthesis were both responsible for the start of the carbon dioxide levels coming down. Now, speaking of photosynthesis, you need to know both the word equation and the symbol equation. Remember that for chemistry, if you're asked to give one, you have to give that one. If they ask you for words, give words. If they ask you for symbols, give symbols. About 1 billion years after the algae, that's when the plants evolved. And eventually, they released enough oxygen that the level got high enough that animals could evolve at that point. Because before then, we're just thinking sort of single-celled organisms and very simple organisms. We didn't have anything that we could really call an animal. So the level of carbon dioxide in the atmosphere was also reduced by the production of sedimentary rocks, like limestone is an example. And in fact, I think it's an example that's named in your spec, so I'm surprised I haven't got it on my slide. And also other organic compounds were turned into fossil fuels. So all those plankton, all those sea creatures died, and they had made their shells from those carbonate compounds. And then after they died, they were covered by sediment, so covered by mud and by sand, and they were exposed to high temperature and high pressure, and therefore were turned into fossil fuels. So the animal plankton are what's turned into gas and oil, and then the plant-based plankton and the algae and things, that's what's turned into coal. So again, all of these contributed to the levels of carbon dioxide in the atmosphere decreasing. So quite often you get little database questions like this talking about how the levels of these gases have changed over time. Obviously you're not going to have colour, but you'd have dotted lines or whatever. So we talk about the fact that for the first chunk of time the nitrogen is rising, and that's because of those volcanoes giving out lots of nitrogen. Then we'd say that carbon dioxide decreases, and crucially, to start with, it's not because of photosynthesis. Everyone says it's photosynthesis, and to begin with, it's not. To begin with, it's the carbon dioxide dissolving in the oceans. And then, at this point, that's when photosynthesis starts kicking in. So at that point, the carbon dioxide is going down and the oxygen is going up. Okay, next up, greenhouse gases. So the first thing we need to clear up is that greenhouse gases aren't fundamentally a bad thing. Okay, so everyone thinks greenhouse gases are just terrible, but if they didn't exist, then it wouldn't be possible for life to survive on Earth because it would just be too cold. So it's worth thinking of greenhouse gases as being a bit like a duvet, right? So if you've got one duvet, you're nice and cozy and happy and everything's good. If you've got a second duvet, it's getting a little bit warm. If someone put 6 duvets on you, you'd be sweating and you'd be really uncomfortable and really unhappy. So that's what's going on now. The levels of greenhouse gases have increased to a point where it's just not a good thing anymore. You need to know that carbon dioxide and methane and water vapour are all examples. Again, that word vapour is really important because otherwise we're not talking about a gas. So the way that this works is that the greenhouse gases form a kind of blanket around the Earth, and shortwave radiation can get through that blanket, and then it's absorbed by the Earth's surface and it's re-reflected with a bit less energy and a bit of a longer wavelength, say as infrared radiation, and that longer wavelength radiation cannot get back out, and so it sticks around and it just warms up the atmosphere. Now, those rising temperatures lead to lots of effects. This is common content with biology, so hopefully you've already revised it, but a few things. If you're talking about melting, it needs to be ice caps, not icebergs, not just ice. An ice cap is millions of square kilometres of ice, whereas an iceberg is maybe the size of your house, right? So when the ice caps start melting, that's going to have a dramatic impact on the Earth's oceans, whereas a smaller bit of ice melting wouldn't have an impact. So definitely ice caps. They lead to flooding. There's also extreme weather events like hurricanes, crop failure and famine. And if you're going to talk about habitat destruction and extinction, we need to be specifying. So we're not particularly worried about, well, we are worried about temperate habitats, but for the sake of GCSE science, we're not worried about what's going on in England, we're worried about what's going on in the Arctic. So talking about polar habitat destruction or Arctic animals going extinct. Okay, so where do humans come into this? So in the last 250 years alone, human activities have led the level of carbon dioxide to increase by about 50%. And a big chunk of that is because of industrialisation and the fact that we've burned so many fossil fuels. So that could be cars, lorries, aeroplanes, factories. And a large proportion of the electricity that we use in the UK is also generated from fossil fuel power stations. And to make matters worse, where in the past a lot of those carbon dioxide emissions were offset by rainforests and other wooded areas, we've been undertaking deforestation on a massive scale, either because we want the timber, we want the wood, or because we want the space, and we chop down the trees so that we can then have farmland there, either growing crops or grazing cattle. So deforestation is also having a massive impact on carbon dioxide levels. And then finally, we've also been digging up peat. So you can think of peat as being a bit like a fancy compost, and we use it both as a fuel and as a fertiliser. And it's a really good carbon sink. It's a place that carbon is locked up, but not if you burn it and let it all out. And then methane is also a really serious greenhouse gas, even if it gets less headlines and less time in the news. And there are 3 big human activities that are all majorly contributing to methane levels. So the first one is cattle farming, which I'm sure you've heard of, because cattle, particularly grain-fed cattle rather than grass-grazing cattle, have a lot of methane in their farts, basically. And so that's a huge contributor to global warming. The second thing is rice farming. So when you grow rice, the plants have to be grown with their roots totally underwater in a rice paddy, and then bacteria live in their roots, and those bacteria anaerobically respire, and as they do so, they release methane, which again is going to contribute to global warming. And then the last thing is using landfill, so using rubbish dumps, and as stuff decays in those, that also releases methane. So why are we interested in what people say about this? So why do scientists publish their data? Why do people believe them? So you need to have this idea that there is a huge amount of data, and lots of different scientific groups around the world have done the same experiments, so what we call peer review, and they found that all that data is reproducible. So when one group of scientists do another group of scientists' experiments and they see the same thing, and so, you know, they've been able to verify each other's data and show that there isn't bias and that this is objective fact, that the level of these gases is increasing, and it's probably our fault, and it's probably going to contribute to global climate change. So, typical exam question might ask you to justify how the increase in the world's population has impacted the greenhouse effect, and the trap that a lot of people fall into is saying, oh, there's more people, so they do more respiration and they breathe out more carbon dioxide. Which is probably true, but is not going to get us our marks. So we need to stick with what it says in the specification. So we want to talk about the fact that all those people need more energy, so they burn more fossil fuels, and they need more farmland, so they do more deforestation. And then in terms of the methane, bigger world population means more food, which I guess is kind of linked to more respiration. So you're going to have more beef farming, more rice farming, and also we're going to have more waste produced, and as that decomposes, then we're going to have more methane being produced as well. Okay, so there are still a few skeptics out there, even within the scientific community, and part of the issue is that people really want us to be able to pin down as an exact prediction for what's going to happen next, and when, and why, and how, but we're actually talking about a really complicated system with hundreds of different variables, and it's really hard to produce an exact model. So what we tend to do instead is to simplify our models, but also people might speculate about what they think might happen, and there can be some biased opinions, and sometimes the media really feeds into this because they say that they're reporting fairly, by which they mean having somebody from both sides of the argument. So you'll have like a breakfast TV show where there's one scientist who says this and one person who says that, and what they don't make clear is that 99.9% of scientists agree that climate change is happening and that it's kind of our fault, and actually the other people are a really, really small minority. So it's really important that wherever possible, we actually look at the scientific data. So yes, you should know that there is a minority of scientists that say there might be another explanation, but basically they're very few and far between, and, well, let's not say anything about who's paying them, but yeah, that. Okay, so you should know that your carbon footprint is the total amount of carbon dioxide and other greenhouse gases that are given out over the full life cycle of a product, service, or event. So we can reduce that either by directly reducing emissions. So in other words, having fewer lorries driving around burning diesel, or by reducing the amount of energy that's used. So things like my computer is currently contributing to global warming because it's using electricity, and that electricity was generated in a power plant, probably by burning some oil or something. Okay, we basically covered all this lot back in Unit 7, but just be aware that these can also come up in Unit 9 questions, so you should know where each one of those pollutants comes from and what the issue it's causing is. Okay, time for a water break. Right, we've finally made it to Unit 10. So, sustainable development is development that meets the needs of current generations without compromising the resources for future generations. So in other words, you using resources in a way that means that there's enough stuff left over that your grandchildren don't have to deal without it. Resources are materials that we can put to use, and for thousands of years humans have made use of the resources around them to provide us with warmth, shelter, food and transport. In order to operate sustainably, chemists seek to use limited resources by like a minimal amount. And they also develop ways of disposing of products at the end of their useful life in ways that ensure that materials and stored energy are utilised. So, resources can be separated into those that are finite and those that are renewable. Finite resources are going to run out because we're using them faster than they're being produced. This might be because they take a very long time to form, or it could be because they're very hard to make. Whereas renewable resources are unlikely to run out because they can be produced faster than we're currently using them. So that doesn't mean that the supply is infinite or endless, it just means that more of it can be produced quite quickly. We can also split resources into those that are natural and those that are synthetic. So natural resources are raw materials that already exist in the world without humans needing to do anything, but they can still run out, and that's why they need to be managed sustainably. That might mean limiting how much people can use, so things like having quotas, or providing additional support to ensure that more of this resource keeps being produced by agriculture, so farming. In some instances, natural materials have been replaced with synthetic materials which are manufactured from chemicals. Synthetic materials often offer greater durability, so that means that they last longer and they don't break down as quickly, and often at a lower cost, and they can help to protect the limited supplies of natural materials. It's very likely in the exams that you get an evaluate question, and I know I've mentioned this loads of times, especially to the kids that I actually teach, but as soon as you see the word evaluate, you have to be thinking compare and contrast. So for instance, if they gave you something like this, we would think about things like how much water it takes to make the different bags, how much can be recycled, how these things break down, and then at the end we would write a conclusion, right? The mark scheme for a question with evaluate as the command word always includes level 3, a strongly justified conclusion. So you need to make sure that you have picked a side, and it doesn't really matter which side it is as long as you then pick some data to back it up. Okay, next up, potable water. So potable water is water that is safe to drink. So it needs to not contain any pathogens, not contain any toxins, and have low levels of salts. So we don't mind a little bit of mineral in there, but not lots and lots, because your kidneys just couldn't cope. It might have some other things in it, like in the UK we add fluoride to about 10% of our drinking water because it's good for preventing tooth decay, and also, you know, we often sterilise water with chlorine, so it would have some of that in that. So potable water is not the same thing as pure water, because as we said in the start of Unit 8, pure water would be just H2O, nothing else added to it. No chlorine, no fluoride ions, no salts. So potable water and pure water are not the same as each other. So, steps to make some drinking water. First up, we need to find a suitable source. So that could be a river, a lake, an aquifer. Sorry, this is for making potable water from fresh water. So that's water that doesn't have any salt in it. And then we're going to pass it through some filter beds to remove some insoluble solids, and then sterilise it to kill the pathogens. So those are microorganisms that could cause disease using chlorine, UV or ozone. So I'm just getting distracted by people diverting people to other people's lives. Cheers, guys. Okay, so that's our fresh water. Now, if we're then thinking about seawater, we sometimes call this saline. As we know, seawater, loads of salt in it, and your kidneys cannot cope with removing that much salt, so you can't drink seawater. So because we sometimes call salt water saline, the process of removing that salt is called desalination. And there are two different ways that we can do it. So first one is distillation, and the second one is reverse osmosis. And both of those are very energy intensive. And the reason we care is because that means they cost more money. But if AQA ask you, why don't we use this a lot? The answer is because they're very energy intensive. They usually don't let you have marks for talking about costs of things. So distillation first. So we've mentioned distillation already in the context of fractional distillation, but essentially we're going to have our salty water in a flask. We're going to heat it up until it evaporates, and then cool it down using a condenser until it condenses, and then we can have our beaker of distilled water at the end. And then reverse osmosis is where we're going to push that salty water through a membrane under very, very high pressure. and the salt can stay on one side and the pure water is forced through. So you've obviously revised osmosis for biology paper 1. Think of it as the opposite to osmosis. So instead of going from where there's a dilute solution to a concentrated solution, which is what happens in osmosis, we're going from a concentrated solution to a dilute solution. And you've still got that partially permeable membrane in between. Okay, and then the last place that we can get water from is wastewater, including sewage. So sewage is wastewater from homes, and it contains toilet waste, detergent and toilet paper. And both sewage and agricultural wastewater, so that's from farms, require taking out organic matter and also harmful microbes. And then we have industrial wastewater, which comes from factories, and to turn that back into potable water, we might need to remove organic matter, so in other words, like leaves and stuff, but also potentially harmful chemicals. So if we're going to treat some sewage, there are 4 steps you need to know. The first one is screening and grit removal. So screening is basically filtering, but just instead of using a piece of filter paper, you're using a metal grid or a metal mesh that stuff is passing through, and that's going to remove big insoluble objects. So that's going to remove things like the toilet paper. Then we spin it in a centrifuge in a process called sedimentation, and that's going to separate it out into the semi-solid sewage sludge and the liquid effluent. Then the sewage sludge is anaerobically digested using bacteria, and the effluent is aerobically biologically treated. So obviously anaerobic is without oxygen, aerobic is with oxygen. So again, this is a prime opportunity for an evaluate question. So again, you need to compare and you need to come up with a conclusion. So we would talk about things like the fact that industrial wastewater is going to require lots and lots of steps. And for groundwater, we would need to do filtering and sterilising, but you would also need to do that for industrial wastewater. You could talk about the fact that purifying water from seawater is only one step, but it's very energy intensive. And then you write a conclusion. And like I said before, it doesn't really matter which one you pick, because you could use the data for to argue either conclusion. Okay, so this is my least favourite required practical, and the reason it's my least favourite is that there isn't just one single practical that you can learn the method for. It's kind of a lot of bitty bits, and I don't really see how they could ask you to write a method for this one. So the practical consists of both testing to see whether a sample of water is pure, and then testing to see what's in it, and then purifying it. So first thing, we know that pure water doesn't contain dissolved solids because it's pure, it's got nothing else in it. So if you're checking about that, what you do is you take a sample of the water and you take a watch glass, like a little glass dish, and you weigh that watch glass and you pour the water onto the top of it, and then you heat that very, very gently over a hot water bath. And at the end of that process, when it's totally dry, you weigh it again and see what mass of solids are left behind. Now, if it's pure water, there will be no solids left behind. If it's water that's got some minerals in it, some salt in it, then you will have solids left behind. It's quite a hard process to do, because if you heat it too vigorously, it will just crack. And if you don't heat it vigorously enough and you leave some water there, then you're going to have a higher mass than you should do. So yeah, not ideal. And the other thing that can happen is, because you have to heat it over a water bath, because that's a very gentle heat, you're then going to end up with a load of condensation on the bottom of it. So if you don't dry the bottom before you weigh it, you would also overestimate how much water, how much solid was dissolved in the water, sorry. Second thing is, you should know that pure water has a pH of 7, so you could use any indicator you like for that. Well, an indicator that shows you where pH 7 is, so I suppose universal indicator is your best bet. So you're expecting it to be green, or you could use a pH probe, which would tell you a number like 7. Also, we know that pure water boils at exactly 100 degrees, so you could heat it up until it boils and take the temperature with a temperature probe. And then if you are doing triple, you could also talk about testing for salt by doing the flame test for the sodium ions and the silver nitrate test for the halide ions. If you're doing combined science, those are not in your specification, you're not supposed to know about them. But if you're doing triple, then they could become relevant. So they could kind of join together this required practical with the ion testing one. And then the second part of this required practical is talking about how you would distill the water in order to make it pure. So we've already seen one setup for it, but here's another setup. So you would have your flask containing your sample of water, and you would heat it over a Bunsen burner so that all the water evaporates, all the salt's left behind, and then it would pass through the condenser into the beaker where you could collect it. And yeah, there's another example of the same sort of thing. So that piece of apparatus that's labelled a condenser, basically you've got a hollow glass tube that your steam could travel through, and then around that there's a kind of jacket that's full of cold water, and it helps to cool it down. So this is the water purification required practical. So you should have tested some water to see if it's pure, but there's a whole bunch of different ways you can do that. Like it's not like the food test required practical where they say test for starch with iodine, test for sugar with Benedict solution. They're just like check if the water's pure, and it's kind of up to your teacher to say what they're going to do with you. Okay, so then we get on to metal extraction. So just as kind of context for this is how the price of copper has changed over the last few years, or at least this was like new and relevant information when I started teaching. It's a bit out of date now, but you can see there that the price of copper has dramatically increased over the years, and the reason for that is that it's becoming more scarce. So most metals are extracted from ores, which are rocks that have enough metal compound in them to make extracting it financially viable, so we can make money from it. Copper is quite an unreactive metal, so it's less reactive than carbon, and therefore you can extract it by reduction with carbon. But if we do that, we're still going to need to purify the product later with electrolysis. When we're thinking about ores, we can split them into high-grade ores, which have quite a lot of copper or whatever the metal is in them, and then also low-grade ores, which have less than 1%. So a low-grade ore, you're not going to make a lot of money from it, but basically we're running out of high-grade ores, so we've started extracting stuff from low-grade ores. And there are two novel methods of getting that metal that you need to know about. So the first one is bioleaching. Remember, B for bioleaching, B for bacteria. So we can use this on low-grade ores, but mainly we use it for cleaning up mining sites. So if you've had a quarry and they've been mining ore, they've been digging up that ore, and then there's usually little bits of metal left behind that they didn't get. So then we can use this bioleaching to get the rest of it. So traditional leaching is chemical based, and it uses cyanide, which is a really nasty poison, and then that's all just left in the environment. So bioleaching is obviously a bit cleaner than that. So your special bacteria go through and they make a liquid called a leachate, and that's going to contain the copper, or contain the metal, and then you're going to get the copper out of that by either using displacement with something like iron, so basically you throw in a more reactive metal and the copper comes out, or by using electrolysis. Advantages are that it has very low energy costs, it doesn't release any harmful gases, so it doesn't release any carbon dioxide, and it's got a high extraction efficiency, so it's good at getting a lot of what's there out. But the thing that is a bit rubbish is that it's very slow. And then we have phytomining with a P, which uses plants instead. So those are special plants that are going to grow on the soil, and they're gradually going to absorb all of the copper through their roots at the same time that they're absorbing water, and then we burn the plants, and we then need to extract the copper from the ash, where, you know, when we burn them, the copper will have all turned into copper oxide. So what we tend to then do is then add some acid to it. So we then get some copper sulfate solution and some water, and we can then go on and do electrolysis, which you learn all about in paper 1. So this is still quite a slow process, but also it has higher energy costs because you're having to burn it, and it does release carbon dioxide, but it's carbon neutral. So what that means is that this plant here, as it's doing photosynthesis, is taking in a load of carbon dioxide, and then when we set a fire to it, we give out the same amount of carbon dioxide. So it's not like where you're burning a fossil fuel and you're giving out carbon dioxide that's been locked up for millions of years and wouldn't be in the atmosphere anyway. You're just putting it back to the point that it would be in if you hadn't grown the plants in the first place. Another advantage of both of these methods is that we're not having to quarry or mine to get the ore out of the ground, so it's not going to destroy as many habitats, it's going to be better for the environment. Alright, let's see what the comments are up to. You can do these processes on other kinds of metal, but I'll be honest, I have never seen an exam question about anything other than copper. So I tend to talk about it in terms of copper. Okay, life cycle assessment. Oh, have I skipped a bit? No. So, life cycle assessment is just a way of analysing the life of a product to see how much water and energy is used and the effects on the environment at different stages. So basically, when you decide you're going to develop a project and you go to the bank to ask for a loan, they want to know how good is it going to be for the environment. So you have to answer a bunch of questions about the different stages of making the product. So the four main stages are extracting and processing the raw materials, the manufacture and packaging, the use of the product throughout its lifetime, and the disposal at the end, and then transport kind of runs through all of those, because obviously you have to transport the raw materials, you have to transport the packaging, you have to transport it to get it to the person who's going to use it, and you have to transport it to the rubbish dump at the end of its life. So, they could sort of ask you for particular types of questions that might occur in an LCA, which one of those categories would it fit into? So things like, where are the materials found? That's about the raw materials. Or things about like, is it biodegradable? Can it be broken down by bacteria? That's about the disposal. So the problem we have with LCAs is that the person who wants to make the product writes it. So therefore, they might not be objective. They might kind of argue more in favour of it being environmentally friendly, even if it's a bit ambiguous and there isn't really a right answer. The other thing is that part of it is about the impact on the environment in terms of things like carbon dioxide emissions. But if you imagine if you were going to, manufacture a computer, and then that computer needed to be transported to a warehouse for storage, there's no way, short of you putting a big balloon on the back of a lorry's exhaust pipe, which I'm pretty sure wouldn't work anyway, for you to actually know how much carbon dioxide that process would release. And when someone uses the computer and they use the electricity that has been formed from burning fossil fuels, actually you don't know how many hours a day they're going to run that computer for. And even if you did, you don't know for any particular day what proportion of the UK's electricity is going to come from burning fossil fuels. It's like if it's a very sunny day, we make more use of solar panels because we can. So it's really hard to actually pin down an exact value for some of these things. So again, evaluate type questions that come up as an LCA. Make sure you're using the data in the table. Make sure you're actually doing something with it. So you can't just state, oh, glass has a density of 2.5, polycarbonate has a density of 1.3. That's not enough. We want to actually do some mathematical operations. So say things like the glass is nearly twice as dense. And then also think about how it relates back to these 5 areas. So the fact that the glass is very dense means that it's going to be heavier. And that means that when it comes to transporting it, the lorry is going to spend more fuel. So that's going to be worse for the environment because it's going to release more carbon dioxide. So yeah, same sort of thing. And again, make sure you write a conclusion. Okay, then we get to our disposal bit. So reducing means sort of cutting down and not buying more stuff than you need. So things like when you go to the supermarket, not buying individually wrapped vegetables, but just sort of having them all in your basket without wrapping them. Reusing would be things like when you go to the supermarket, taking a bag for life with you and just using it over and over. And then recycling is specifically when we're processing something to make a new product. So, melting it down or tearing it up or mixing it with other things. There's got to be some processing involved. Now, there are lots of good reasons for us to revise. There's the fact that it's going to save us some money because raw materials are scarce and expensive, and it might be cheaper to recycle them than to extract new. Now, that's not always true. So things like aluminium is really expensive to make from scratch. It's a lot cheaper to recycle. So that's why we are really good at recycling cans. Whereas plastic, it costs about the same. So that's why even if you as a human at home put your plastic into the recycling bin, there's a very good chance that it doesn't actually get recycled because the difference in cost doesn't really make it worthwhile. Recycling is also good for the environment because it has lower energy costs and it requires less mining, so that's going to disrupt less habitats, and it requires less landfill space because waste is being recycled rather than just put in landfill. And also it's just socially a good thing to do. So recycling is more sustainable. That idea about us leaving resources that are available for the generations that come after us. Yeah. I'm going to give you someone else is going to have to leave a comment because I can never read the very last comment that's been left. So I know that Monterayo has left a comment, but I don't actually know what it is. But I'll come to it once someone comments something else. Okay, so you need to be able to discuss the recycling of aluminium and glass and paper. So when metal's recycled, it's often just all stuck in a box together. So the first thing that we need to do is to remove any iron or steel, which we can do with magnets. And then we get the aluminium cans and we squash them and shred them into little pieces, blast them with hot air to remove any labels or ink. And then we feed them into a furnace at about 750 degrees C, which is hot enough to melt the aluminium. And so any impurities in there, which we call dross, rise up to the surface and they can be scraped off. And the pure aluminium cools down and is cast into metal blocks called ingots, which are then sent off to a rolling mill where they can be flattened out into thin sheets for making new cans. Density question about copper. It'll be something to do with comparing it to another material. So I can't think of a good one, but maybe something like if you were going to make a tennis racket out of carbon fibre versus copper. I don't know why you would make a tennis racket out of copper, but let's just go with it. So if the copper is denser, that would make it heavier, and so that would make it harder to use. It's usually either to do with how difficult it is to transport or how difficult it is to use. Okay, so then we get on to our glass. So again, we need to separate it out from sort of paper and cans and other stuff that's recycled at the same time. Then we use lasers to colour sort it. We crush it up to make teeny tiny bits of glass that we call cullet, melt it in a furnace at about 1500 degrees C, divide it up into gobs, which are sort of blobs of melted glass, and then blow it out into new bottles and jars. And then recycling paper and cardboard is often quite a lot harder than glass and aluminium for two reasons. So one is there are so many different types of paper and card and they all have to be recycled in different ways. And it's a lot harder to sort those out. So whereas you can use a laser to sort the different colours of glass into different colours, you kind of have to use a human to go through your paper waste and say, oh, this is copy paper and this is cardboard and everything. And then the other thing is that whereas you can just keep recycling aluminium over and over and over and it's still good, with paper, each time you recycle it, the fibres get shorter and the paper gets weaker. And so actually you can't really have just recycled paper. They sort of tend to, even recycled paper is made out of 50% recycled paper and 50% virgin fibres, like brand new paper, because otherwise it just falls apart basically. Yeah, so basically we separate it all out, shred it up, give it a clean, screen it, so again pass it through that mesh grid to remove any paper clips or staples or anything, then add in some new virgin fibres and press it to form new paper. So they quite like to give you sort of like, suggest questions about why it's difficult to recycle. So things like milk bottles with green lids, it's really hard to recycle them because if you just melt down the milk bottle, you get slightly greenish plastic and nobody wants to buy it. And copper, even though it's worth loads of money, there isn't a way to easily separate it from other metals. So again, you're relying on humans to go through and hand pick it, and that makes it really expensive. So yeah, we've sort of said you could be asked about why it's good to recycle. So we could talk about resources being limited and space at the landfill site being limited, and also the fact that metal is going to have fatigue over time. So if you just try and reuse something, it could actually be dangerous depending on what you're using it for. Okay, we're now on to triple science stuff again. Unscheduled water break. Okay, so there are, when we talk about corrosion, we're talking about substances being destroyed because they're reacting with chemicals in the environment, usually oxygen and water, but it could be other things as well. So rusting is one example of corrosion, but there are two important things to bear in mind, because rusting only applies to a very narrow window. It has to be iron. So these copper nails have not rusted because they're not made of iron. They're made of copper. So we say they're corroded instead. And the second thing is that when something rusts, when an iron object rusts, it reacts with oxygen and water. So there are a number of different ways that we can stop an object from corroding or from rusting, and they mainly revolve around stopping oxygen or water from getting to the metal. So in the top right here, I've got an iron nail, and because it's not currently protected, over time it will rust. So look, it's gone orange. If I use a barrier method, then that would stop oxygen from getting to it. So that could be greasing a bike chain, painting some railings, electroplating cheap earrings. You know, like when you buy Claire's Accessories earrings and they turn your ears green after a little while? It's because they've got a very thin layer of silver over the outside of some copper. And once the silver has kind of worn away and the copper can get to your ears, then it starts oxidising and that's why it goes green. So a barrier method will stop the metal from tarnishing and corroding. So you can see my second nail here, it's got this layer of red paint around it, and therefore it doesn't rust. But the thing with barrier methods is they only work for as long as the barrier remains intact. So if you get a scratch in the paint, like my third nail here, that one can still rust because now the oxygen can get to it. Also, some metals form their own natural barrier, and aluminium is one example of this. So aluminium reacts very quickly with oxygen to make aluminium oxide, and aluminium oxide is very resistant to corrosion. So then no more oxygen can get to the aluminium because it can't get through the aluminium oxide. Then we've got galvanising, which is a little bit different. So this is where we use a more reactive metal we call it sacrificial protection. Basically, the oxygen reacts with the more reactive metal, or the water reacts with the more reactive metal instead of the metal we're trying to protect. So they do it sometimes with ships where they have a big block of magnesium with them that they're kind of dragging through the water, and the water reacts with the magnesium instead of with the ship. But again, this kind of can run out. So this here is my incinerator, which was galvanised. So it had zinc in with the iron, and the oxygen would react with the zinc instead. But eventually, all of the zinc had oxidised, and so the oxygen then started reacting with the iron, and eventually it just went really rusty. So this is a really classic experiment that's come up quite a few times. So we've got a bunch of different nails in different tubes, and we're describing what would happen to each one of them. And so the point is that in order for it to rust, it has to have access to oxygen and water. So first one will rust, it has oxygen and it has water. Second one won't rust because water can't get in. Third one is covered in paint, so it won't rust because oxygen can't get in, and water to be fair. Fourth one is covered in paint, but it's got oh, words, De Bruin, what are you doing? The paint has flaked off at one point. It's got a scratch in it. So the oxygen can get in, so it will rust. The fifth one has been galvanised, so that's why it's darker and why it says number 5, galvanised nail. So it won't rust because the oxygen will react with the zinc instead. The sixth one still won't rust because as long as the zinc is anywhere on there, it will be oxidised preferentially. So unlike the paint, it doesn't matter if it gets scratched. And then the last one won't rust because oxygen can't get in. Okay, so we met alloys in Unit 2 and we talked about all that lot, and we also talked about it briefly in Unit 8. You need to be aware that alloys are an example of a formulation, so we talked about this in Unit 8 as well. But then the triple bit special is that we have 7 named alloys. So bronze is an alloy of copper with a small amount of tin, and that was what we used to use to make 2p pieces up until 1992 when copper got too expensive. Then the second alloy is brass, which is used to make the pins of electrical plugs. It's got a lot of copper and a little bit amount of zinc to harden it so that the plug doesn't bend when you stick it in the wall. Some jewellery is made out of pure gold, but the majority is made of gold alloys, where the gold's been mixed with other metals to make it less soft, so it's less likely to get dented or scratched or damaged. And also, alloying gold allows us to have different colours of gold, like white gold or rose gold. We assess the purity of gold using a carat system. So 24 karat gold is pure gold, and then anything else you can work out as a percentage based on that. So 18 karat gold is 75% gold, and 25% will be other metals like silver and copper and zinc. Then steels are a group of alloys based on iron, and they contain specific amounts of either carbon or other metals. So high carbon steel, as the name would suggest, has quite a lot of carbon in it, and that makes it very hard and very strong, but also quite brittle. So if you push it from the side, it could fracture and it could break. So we tend to use it for things that need a high amount of force, but it's always in a predictable direction. So things like cutting tools, drills, where it's just going up and down in a factory and it's never having sort of an unexpected force acting on it. Whereas low carbon steels are softer, so they're more easily shaped, so we can use them for things like making car bodies. Stainless steels resist corrosion, so they're useful for making cutlery, because lots of our foods have acids in that would eat away and tarnish just pure iron cutlery. And then you also need to know that aluminium alloys are very low density. If you think about where aluminium is on the periodic table, it's really near the top. It's got a much lower mass compared to things like iron, and so that makes it really useful for things like making aircraft. Okay, so then ceramics are non-metallic solids that are usually made from a raw material that is heated to a very high temperature. And there are two types that you need to know about: clay ceramics like pottery and glass. And the key difference is that clay ceramics are made in a furnace from clay and they're opaque, whereas glass ceramics are transparent. And that will affect what you're going to use them for, whether it's important to be able to see through something or not. They're both hard and they're waterproof, but they're brittle and they shatter easily if you drop them. You could be asked about the use of ceramics and what properties they have that makes them appropriate for that use. So for instance, we said they're waterproof, so therefore they're useful as bathroom tiles. And it doesn't really matter that they're quite fragile because they're glued onto the wall. Then the glass ceramics we can split into two types. There's soda lime glass, which is used for everyday uses like making windows and tumblers for drinking out of, and it's made from sand, sodium carbonate, and so that's the soda bit, and limestone, so that's the lime bit, hence soda lime. But it doesn't have a very high melting point, and that could be problematic if you want to use it for something that's going to reach a very high temperature, so like lab use. So for things that are going to get hot, whether that's using them in a chemistry lab or using them in a kitchen, you use borosilicate glass, and that's made from sand, so that's the silica bit, and boron trioxide, which is where the boro part of the name comes from. Again, we've mentioned polymers, but we did say that there was some more new stuff that's in Unit 10. So polymers can have different properties, like different melting points, and the properties will differ partly based on the monomer. So if you're making it out of a different chemical, it's not going to be the same, it's not going to have the same properties, but also the reaction conditions, which include the temperature, the pressure, and the catalyst. Ceramics are poor conductors of electricity because they haven't got any charged particles. Okay, so classic example of polymers with different properties: low density polyethylene and high density polyethylene. So low density is made under super high pressure, pretty high temperature, little bit of oxygen in there as a catalyst, and when the polymer forms, it makes branches, and those branches stop the chains from packing too closely together. Whereas high density polyethylene is made under relatively low pressure, so I mean it's still 10 times higher than the pressure in the room right now, but compared to 1,000 for the LDPE, slightly lower temperature, and a catalyst called a Ziegler-Natta catalyst. And when it forms, the polymer chains get into these really regular rows that pack tightly together, and so the final polymer is much harder and also much denser. Then, totally separate from that, you also need to know about thermosetting and thermosoftening polymers. So if you look at a thermosetting polymer on a molecular level, it looks kind of like a wonky brick wall. They have cross-links between the chains, and those cross-links are covalent bonds. So they need a huge amount of energy to break, and that just doesn't happen. And so that means that your thermosetting polymer, if you heat it up, it doesn't melt, it just eventually chars. whereas thermo-softening polymers don't have crosslinks. They don't have covalent bonds attaching one polymer chain to the next one. And so that means they do melt when the temperature gets high. So thermo-softening polymers are absolutely no good for anything heat sensitive. Like if you had a saucepan and you want to make a handle for the saucepan, there's no good making it out of a thermo-softening polymer because it would just melt off. Then we have our composites. So you make a composite material by combining two or more raw materials, but like not mushing them all up totally together. You're still going to distinctly have areas of each material. And we call the two parts the support, so that's the bit that is like providing the structure, and then the matrix or the binder, which is what's going to kind of hold the whole thing together. We've got a couple of different examples that we need to talk about, and the point with these examples is that the composite material has some properties from both of the bits that make it up. We've got some natural examples and some synthetic examples. So wood is an example of a natural polymer. It's got that soft cellulose that's found in all plant cell walls, but it's combined with lignin, which is harder. So the lignin fibres form the reinforcement or the support, and they're surrounded by the cellulose matrix. Then examples of synthetic ones, so steel reinforced concrete has concrete, which has really good compressive strength, so it resists being squashed, but if you try and bend it, it's fragile, it shatters. So the steel reinforcement has really good tensile strength, which means you can stretch it and bend it, and so it's able to resist that. So steel reinforced concrete is even stronger and better than just regular concrete because it resists being squashed and it resists being stretched even. Plywood is another example, so where you've got very thin layers of wood held together with glue, so the plywood is the reinforcement and the glue is the matrix. Okay. The Haber process is an industrial chemical process that was developed by Fritz Haber in the early part of the 20th century as a way to make ammonia, which is the main component of most of the fertilisers that our farmers use on their crops to make sure that their yields are high enough that they can grow enough food to feed everybody. And Haber actually won the Nobel Prize for his work to develop this process. At the same time, you can use ammonia for some slightly less nice things like making explosives and chemical weapons. Ammonia is one of the 8 named examples of small covalent molecules that you drew in Unit 2, and this is a quick reminder that stuff from Unit 1, 2 and 3 can come up in Paper 2 as well. Not for a big question, but for little 1 or 2 markers, those fundamental topics, it does say in the front of your spec, they can be examined in either paper. So just bear that in mind. So when ammonia boils, it's not the strong covalent bonds inside the molecule that break, it's the weak intermolecular forces between the molecules. So ammonia is a gas at room temperature. It's made out of hydrogen and nitrogen, which are also gases, reacting in a 3-to-1 ratio, which we can see in the equation there, and it's a reversible reaction, which you can tell from the funky arrow. To make the ammonia, the nitrogen that we're going to use is extracted from the air, but it does need to be separated from the other gases, because if there was oxygen in there as well, the oxygen would just react with everything and ruin it all. And then the hydrogen can be made in a few different ways, but most commonly by reacting methane with steam. So for the reaction to take place, the mixture of gases in that 3-to-1 ratio are fed into the reactor, and there they react together in the presence of a hot iron catalyst at a temperature of 450 degrees C and a pressure of about 200 atmospheric pressures. The iron catalyst is used because it helps to speed up the rate of reaction without needing to heat things up further, and that's going to help reduce energy costs and be better for the environment. The other 2 conditions are both compromises, and this links back to Unit 6, and you do need to be able to talk about them. So in Unit 6 you learned that a reversible reaction can reach equilibrium where the 2 reactions are happening at the same rate. And Le Chatelier's principle tells us that if we make a change, the system will shift to counteract that change. So if we increase the pressure, the system will try to decrease it. If I look at my equation for the Haber process, I can see that on the left-hand side, I've got 5 moles of gases, and on the right-hand side, I've got 2 moles of gases. So therefore, if I increase the pressure, to decrease the pressure, I'm going to favour the forward reaction. So high pressure is also going to give me more yield. But high pressure is dangerous because it's more likely to explode. Try and give as much detail as you can, right? Don't just say, oh, it's dangerous, say why. And also it's more expensive because you're going to need equipment that can cope with being at 200 atmospheres. So we pick a pressure that is basically as high as we can afford to. If we pushed it higher, we could have a bigger yield, but it would be more dangerous and more expensive. And then temperature is a bit more of a nightmare. So we said that in a reversible reaction, one reaction is always exothermic and one reaction is endothermic. So this reaction, the forward reaction, is exothermic. So the forward reaction gets hotter. So if I increase the temperature, that will favour the endothermic reaction, which gets colder, which here is the backwards reaction. So in other words, it's going to make that happen. So I'm going to make less ammonia if it gets hotter. So then you would think, well, why not do it at a very, very cold temperature? Because then we'll get lots of ammonia. Right, so you can see here on the graph that as the temperature gets hotter, the amount of ammonia is going down, right? So you would think, well, why not use a cold temperature? But the problem is that cold reactions go very slowly. They have a slow rate. So we would make more ammonia, but it would take us all year. So again, the temperature is a compromise. And if I use about 450 degrees, that means that I can make about 17% ammonia, which is about enough to make it economically viable. Now, because only 17% of that nitrogen and hydrogen are reacting, what comes out of the reactor is a mixture of gases. So we put them into this condenser here, so this is very, very cool. And we cool the mixture so that it's cold enough that that the ammonia has become a liquid. So therefore it has to be below minus 34, or so I suppose below minus 33, which is minus 34. I'm confusing myself now. But it needs to be warm enough that nitrogen is still a gas. So it's going to be in that gap there. And then the ammonia is going to be removed, and the leftover hydrogen and nitrogen is just going to be recycled back into the reactor there. So we said that one of the biggest uses for ammonia is in fertilisers. So you should know about NPK fertilisers. So those three are the chemical symbols for nitrogen and phosphorus and potassium, which are all things that plants need. And if they don't have enough of them, that would reduce the yield. But if we do add fertilisers to our crops, they cost a lot of money. It costs a long time to spread them on, and also if it rains, then the fertiliser can run off into the waterways, so run off into nearby lakes and rivers, and when that happens it can trigger an algal bloom where all the little green algae go, ooh, tasty, tasty fertiliser, and they grow like mad. And then when they run out of nutrients and they die off, bacteria come and break them down, and in doing so they use up all the oxygen in the water and they deoxygenate the water, and then everything dies. So NPK fertilisers are an example of synthetic fertilisers, so they're made from chemicals, and they're formulations, so we know exactly what proportion all of the different compounds are, and they contain salts of nitrogen, phosphorus and potassium, so they're not going to contain just those pure elements. So we add nitrogen in the form of ammonia. We can mine potassium chloride, potassium sulfate and phosphate rock. The potassium chloride and the potassium sulfate are soluble, so we can just put those in the fertiliser, but a phosphate rock is a rock, so you can't put it in. So what you do is you break down that rock by using nitric acid, or less commonly sulfuric acid, and that produces phosphoric acid, and then calcium nitrate or calcium sulfate, which is, what we're going to be left with. So again, you could get some sort of suggesty, evaluatey type questions where they ask you about different fertilisers and whether a farmer would need to use one or both of them and why he might choose a certain way. So here we could say that making ammonium phosphate takes more raw ingredients because you've got the sulfuric acid and the phosphate rock and the ammonia, and there's more processes involved. But also you're going to need both of those chemicals because the crops do need nitrogen and phosphorus and potassium, and if you don't have the potassium chloride, then you don't have any potassium in there, so that's no good at all. This is also a really good example of where they can throw in some more maths skills, so you know that your maths marks are 20% of the paper. So things like just asking you to work out a simple percentage, and if they're feeling mean, they could also ask you to convert, so putting it into grams. Also doing similar sort of things with ratios, so working that sort of thing out. And that is us done for content. So a couple of last little reminders before we call it a day. If you haven't been already, please write in black pen. Your paper is going to be scanned. If it's not in black, it makes it really hard to read it. Make sure you stay inside the box because they're going to chop off the margins. So if you write outside the box, your marker might not get to see what you've written. Watch out for sneaky units. Less relevant for this paper, to be fair. If you're writing an extended response question, bullet points are not just allowed, they are encouraged. They make your marker's life easier. I'm sure I've emphasised this enough tonight, but just in case, for the final time, if you have an evaluate question, you must compare the data and you must write a conclusion. If you do not write a conclusion, you cannot have the last 2 marks. If you do write a method, particularly for those Unit 6 practicals, make sure that you've identified your variables and that you've written a method that would work. So it will actually allow you to answer the question. So your variables, remember mix dry, you modify your independent variable. If you're drawing a graph, it goes on the x-axis. Your dependent variable is the one you record, and that goes on the y-axis. Control variables are to make it a valid experiment. If you do the same experiment and you get the same results when you do it again with the same method, that is repeatable. Whereas if somebody else does some peer review and they get the same pattern of results, that's reproducible. Resolution is the smallest measurement that your equipment can measure the difference between. So that could be for something like a temperature or for a measuring cylinder. Computerized instrumental methods are accurate, rapid and sensitive. And if you're drawing any graphs, your line of best fit doesn't have to be straight. Systematic errors are caused by your equipment being poorly calibrated, so where it's always out by the same amount and you can just correct by, say, subtracting half a kilogram each time, whereas random errors are caused by your equipment not being precise enough and by natural fluctuation in the value. So in order to do that, you would repeat, you would remove any anomalous data, any data that doesn't fit the pattern, and then you would calculate a mean. And then last but not least, mathematical requirements. So we've mentioned these are going to make up 20% of all the marks in the paper. So decimals, I'm sure we're all fine with. Standard form, make sure you know how to use your calculator. Make sure you know where your times 10 to the whatever button is. Fractions, ratios, percentages, estimates, significant figures. Watch out for those because they're always worth a mark. Calculating means, I haven't seen any medians or modes in ages, but they are listed in there. Frequency tables, bar charts, you know, if you're drawing bar charts, make sure you're leaving spaces between the bars, make sure you're using your ruler, which I'm currently not. Histograms, scatter diagrams, orders of magnitude. These symbols here, if you haven't seen them already, I'm sure you know less than, but if you've got a double less than, it just means a lot smaller than. The fish alpha thing is directly proportional, and the little wiggly line is a tilde, and that means approximately. Changing subjects of the equation, probably not so relevant for chemistry paper 2. Likewise, substituting and solving equations, and then converting between graphs and tables is just, can you take a table of data and plot it on a graph? And that's the whole lot. So yeah, good luck and thanks for all the fish. I'll hang around for a little while, so if anyone does have any other questions or bits they want me to go back over, that I can do. But if not, good luck for the exam on Friday. I'll just pop it back to the screen I showed right at the start with all the other resources, just in case any of these are useful to you. So if you weren't with us at the start, this is the pre-recorded one, which is only about 70 minutes long. These are questions if you want to check that you've memorised all the facts from the spec, and these are the answer videos where I go through them. This is a new video from this week about the required practicals, so there's a method for each one of them and also just talking through them, and then these are individual unit summaries for each unit. So if you joined us after the first unit and you want to go just revise unit 6, you can find that playlist there. All of those links are in the description. And if not, then thanks for coming along. I would just say that carbon monoxide is toxic, because that's all that your spec says. chemical analysis is quite a big topic. So if you are if you're wanting to do the whole topic, what I would do is go to this address here. It is case sensitive, so you need to have the capitals in the right place, or there's a link in the description that you can click on, and then watch the chemical analysis video, which is about 15-20 minutes. What do I mean by compromise? So compromise means, like if you think about the temperature for the Haber process, if you have a really low temperature, you'll make lots of ammonia, but you'll do it really slowly. If you have a really high temperature, you'll make hardly any ammonia, but you'll do it really quickly. And we want to make lots of ammonia and do it fast. So instead, we pick a temperature in between where we make quite a bit of ammonia and we make it quite fast. Okay, so it looks like everyone's pretty happy. So good luck with the revision, folks, and yeah, see you soon.